Okay, that was Yanni going out to Manu from WCPAESS.
I bet you nobody knows what that is.
Well, they've been participating in a CPAS event all for the last couple of weeks. So you can pick out all the station call letters that I've been using. I've been making up as we go along. Anyway, welcome back for today. Today is our our last major lectures today. Today is Ionosphere Day, Day of the Ionosphere. And so we're going straight into Shasha's lecture. I'm going to turn it over to Mark, who will be moderating for the first two sessions today, and
Great.
uh, we'll get right to it.
Good morning, Sasha. A long time no see, even though our offices are technically in the same hallway, but with summer and COVID, it's been an interesting time. I'll be helping monitor the chat so you can focus on your Zoom controls. But if you don't mind, I can interrupt you if there's a question in the chat to answer. We have, I think we're getting there. We have most of the students have joined us, but if you want to try sharing your screen and get started and introduce yourself.
Okay, so can you see the slides?
Yep.
Is this the full screen?
It's full screen.
Okay, perfect. Hi everyone. Hi, I'm Shasha Zhou from University of Michigan. As Mark just mentioned, our office is just across the hallway from each other. But I'm teaching from home today. Okay, let me adjust my camera and other things. Okay, so yeah, it's great to come back. You know, I was teaching here in the Heliophysics Summer School last year, and I enjoyed it very much. And so this year, Mark asked me to again, and so I'm like, yeah, why not? So yeah, it's great to see everyone virtually. Of course, most of you just have your pictures or black screen, but you know, feel free to turn on your camera if you want, and it always feels better to see your face. You know, either you like it or you don't like it, but it's better that I can see your reaction. So I have been teaching ionosphere and thermosphere classes here in Michigan for the last several years. Today I will talk about some of the most important, in my mind, the fundamentals about thermosphere and ionosphere. We start with the basics, and then in the second part of the lecture, and I want to move on to the more interesting and more dynamic ionosphere and thermosphere, like during storms, those things. So, okay, let's get started. And Mark, feel free to stop me, you know, if you see any questions in the chat. Yeah, I think it's better to go that way. Yeah. Okay. So let's go. So first I want to play a really nice visualization that is generated by the NASA Scientific Visualization Studio. This is a really nice video, gives you an idea of what the ionosphere and thermosphere, you know, actually look like. So once I click the start button, you will see now it will become a lot more colorful, and then color actually represents the atomic oxygen density in the ionosphere. So you are looking at somewhere around 300 kilometers, and you will see that red means high density and the bluish means low density. Okay, and those lines are the Earth's magnetic fields near the equator and the low latitude region. Okay, so here we go. Can you see the video playing? Okay, perfect. So now we are on the day side, right? So you see this reddish bands in both the northern and the southern hemisphere, this is probably the largest scale structure existing in the ionosphere, and it's called the equatorial ionization anomaly. Although we call it anomaly, but it actually occurs almost on a daily basis, so it's not really an anomaly. It was just a surprise when people discovered it many years ago. So besides the density of the atomic oxygen, you see a lot of vectors there as well. This one, the purplish color actually the thermospheric winds around 300 kilometer altitude, and they're also white and smaller vectors. This is the wind around 100 kilometers. So this video tells you that our ionosphere and thermosphere is a highly dynamic environment. And another important information is that the thermosphere and ionosphere coexist in the same space. And that is a very important concept. They share the same space. Okay. So next, let's look at the definition for the thermosphere and ionosphere. The thermosphere is a continuation of our troposphere, stratosphere, mesosphere that you are more familiar with probably. And those spheres are based on neutral properties. And more specifically, they're based on the temperature gradient of those neutrals. So thermosphere refers to the layer starting roughly from like 80 kilometers. That's the coldest part, that's a mesopause. And starting from there, you can see the temperature increase significantly in a very narrow range from like 80 kilometers all the way to about 200 kilometers. And then the temperature shoots all the way from below 300 Kelvin to almost over 1,000 Kelvin, right? So there is a really significant heating that is going on in this region that gives you this sudden temperature increase in that region. And so the thermosphere refers from this mesopause all the way to like 500 or 600 kilometers. And above that, it becomes the exosphere. And that is a region where the collisions between the particles become so insignificant, and then they almost only collide once when they move up one scale height. So that's the definition of the exosphere. So thermosphere is this one layer here in the middle, okay? And it's important to remember that the definition is based on the neutral temperature gradient. Now the ionosphere exists in the same location, but they refer to the plasma structures, and then the different layers in the ionosphere are defined based on the plasma density peaks, the local peaks. The two most important layers that people are often talking about and occurs most often are the E region or E layer, and then the F layer. The F layer is usually the region where the largest, the highest plasma density occurs in the ionosphere. So this F region peaks around 300 kilometers around that altitude. So from this very simple chart, you can see the thermosphere and ionosphere share the same space, but then they are defined based on, one is based on neutral temperature gradient and another one is based on plasma density, right? So it's very important to understand how they are defined. Now here, I'm borrowing this picture from the NCAR HAO's module, and then it shows the empirical model for neutral. So that's MCIS, and then the empirical model for ionosphere, IRI model. What is shown here is around the mid-latitude on the day side during solar max. The blue line is the electron density, and then the yellow or orangish line is for the neutral density. So if you compare the magnitude of those two densities, you will see that in the E region, the electron density is about 5 orders of magnitude smaller than the neutrals. And even in the F region, it's still about 2 to 3 orders of magnitude smaller than the neutral density. So this tells us the ionosphere is a weakly ionized plasma environment. And because the number density is much lower than the neutrals, so the ion and the neutral collisional coupling strongly modulates the ionosphere and thermosphere dynamics. And this also tells us why the thermosphere is actually considered as the ultimate energy sink in the geospace system. It's just because of the number density there. It is much larger than the ionosphere. The neutrals cannot feel the magnetic field, or they cannot feel the electric field. And so they need the ionosphere to convert the electromagnetic energies and the through collisions into the neutrals' thermal or mechanical energies. You will see that later. But the most important point from this chart is that the ionosphere is a weakly ionized plasma, and the collisions in both the E and F region are important, especially in the E region. So next, let's look at the thermosphere composition. It's pretty sunny here in Ann Arbor. I don't know what happens, the weather looks like in your area, but no matter what the weather looks like, if you look outside, the atmosphere, just outside our window, are many N2 and O2, molecular species, right? Nick is showing the weather. It looks like cloudy-ish in Boston, if you are in Boston. Yeah, I was actually in Boston last week. It was really hot and humid.
Well, it's still humid. It's just not so hot.
Okay. Yeah. So no matter what happens, but it's many N2 and O2, okay, molecular species. The interesting thing about the thermosphere is that once you move to higher altitude, you start to see the atomic species becomes more and more important. First, it starts with atomic oxygen, and at a higher altitude, somewhere about 400, 500, you start to see helium and hydrogen become more important. So we will see in the next couple of slides why those atomic species shows up, even though, just outside our window, they are actually not significant in the lower atmosphere. So on this slide, one of the important concepts I want to mention, and I think many of you probably have already learned about this, is the scale height, right? The scale height, H here, is determined by the neutral's temperature and the mass, basically. And then the K and G here are just the constants that are listed here. So the higher the neutral temperature, the larger the scale height. And this is the parameter that controls how fast the neutral densities change as a function of altitude. And how do they change? It is according to this very simple equation here. So the density decreases exponentially, but the rate is controlled by scale height. So the higher the temperature, the larger the scale height, then the slower the density decreases when you move to higher altitude. So in the later you will see that when the solar radiation variation that controls the new thermosphere temperature, and that again controls the density. So you will see that how the solar conditions will modulate the thermosphere density and temperature later. Okay. Is there any question in the chat?
Nope, not yet.
Okay. So why atomic oxygen species and atomic H shows up at higher altitudes in the thermosphere? We need to look at the absorption of solar radiation. The solar radiation, including both the EUV and then the FUV wavelengths, are the most important energy source for the thermosphere. And they can dissociate the molecular species into atomic species. And that is why, we start to see the atomic species in higher thermosphere, in higher altitude. Besides the photodissociation, they can also heat those neutral gases and then produce the ionosphere, by ionizing those neutrals. The picture on the right here shows the incoming solar wavelengths. We are looking at actually from almost close to soft X-ray or X-ray to about FUV range, 0 to about 300 nanometer wavelengths. And this is the most important range of the solar radiation for the thermosphere, right? Okay, and then here at the top, you can see that it labels N2 or O or O2. This one actually tells you this is the wavelength range that those neutrals will absorb the solar radiation. And then this curve here tells you the peak altitude where that absorption occurs. So for example, the N2 and O absorb the solar radiation, from below 100 nanometer all the way to close to like 20 nanometers. And then that peak absorption occurs like around 160 kilometers. So this is how you rate this chart. And from this chart, you can see that the O2, N2O, and O2 in the thermosphere, which are the most abundant, species, they absorb the solar radiation mainly between this 100 and to 200 kilometer altitude. If you still remember the several slides earlier when we defined the thermosphere, I mentioned that the thermosphere temperature increased significantly within this layer, right? And this is why it happens in this very narrow range, because that's where most of the photoabsorption occurs, and they are absorbed by the most abundant thermosphere species. Now, there are other information that you can get from this chart as well. For example, those little arrows, indicate very discrete wavelengths, and those discrete wavelengths refers to the ionization energy that's needed and to ionize, for example, atomic N or atomic O. And this information would be useful when we start to talk about how the solar photoionization turns the thermosphere into ionosphere part. But here, this chart basically tells you that the photodissociation within the range of 100 and 200 kilometers is the most important reason that we can see atomic oxygen and hydrogen species in the upper thermosphere. So here are a little bit more details about the photodissociation process. I listed the most important chemical reactions that produce those atomic species. And so here you can see that one of the solar photons that can be absorbed by the molecular species, and the photon breaks the bonds of the N2, and so generates 2 atomic oxygen. The energy that's needed for these chemical reactions to occur is about 5 eV. Okay, and then for different photodissociations, you will need different energies. So the N2 needs a little bit higher, close to 10 eV, and then to generate 1 atomic hydrogen, you need about 4.7 eV, right? So those chemical reactions here are the most important ones for photodissociation, for generating atomic species in the thermosphere. This slide is just for your information. It summarizes how the number density, the mass density, and also the AMU basically changes as a function of altitude and for different neutral species, I found this is a very interesting, very informative slide, and so I listed here as a reference. Now, because the solar EUV and FUV radiation is the primary heating source for the thermosphere, so you can imagine that the day side regions that's facing the sun will be heated up quickly during the day, and also in the summer hemispheres it will absorb more solar radiations, right, just because direct sunlight. So that basically gives you the seasonal variation of the thermosphere temperature. And as I mentioned, the neutral density is controlled by the scale height, and which is controlled by the temperature. So this one also gives you the seasonal thermosphere density variations. During equinox seasons, the heating received by the two hemispheres are roughly the same, and so you see a hemispheric symmetric pattern. We have higher density on the day side and lower density on the night side. Not surprising, right? So for solstice, and the coldest part or the lowest density part would occur just before sunrise after that long and dark winter night, right? So this chart summarizes the seasonal variation of the thermosphere density, but the temperature is also similar to this pattern. Now we look at the seasonal variation. Let's look at the solar cycle variation of the thermosphere. Again, because the solar radiation itself has clear solar cycle variations, we get more solar radiance during solar max, and then smaller solar radiance during solar mean. So the thermosphere temperature and density directly reflect that solar cycle variation. You see in this chart, the yellow line indicate the temperature and the density for solar minimum condition, and the red curves here indicate for solar maximum condition. So during solar maximum, you see that the temperature increase by 2 or almost to 300 Kelvin. That's a significant increase, and directly reflect to the density. So you see the density also increases, right? So those are all controlled by the solar radiation variation itself. So next I'm going to talk about the ionosphere, but before I start the ionosphere, I want to see whether there are questions about the thermosphere.
How does water get into the thermosphere?
So the water is an important species, molecular species in the lower atmosphere. And then in the lower atmosphere, if I go back here, in the lower atmosphere, all the neutral species, their densities changes according to the mean mass, and they share the same scale height. And so we have some water species that's happening in the density also decreases as a function of altitude, but there are still some of them that can reach the mesopause, right? And the mesopause is a very interesting layer. That is a layer that has a lot of turbulence going on, and what we call the turbulent mixing. And through eddy diffusion and other dynamic process in that layer, the heavier but molecular species can get into the lower part of the thermosphere.
Great. And then Miguel has a question. Do you want to unmute, Miguel? Or I can ask for you, why is there an increase of density at solar maximum at high altitudes?
This one here?
Yes.
Yeah. So for solar max, you can see this red curve here. The temperature increased, right, comparing with the solar minimum. And this temperature increase directly increase the scale height. So according to that equation I just showed, the density will decrease slower if you increase the scale height. And so starting from about here, you see there is very little density change in the lower altitude, but then the density decreases slower as you move to higher altitude. This is why in the thermosphere here, we see the density is higher during solar maximum comparing with the solar minimum. It is because of this temperature change and then the scale height increase.
Can I ask one more quick question?
Sure.
Would you mind going back a few slides to that really neat plot that had wavelength versus altitude? This one, yeah. I'm a little bit confused by the Lyman alpha being around or below 100 kilometers because hydrogen, shouldn't it be what's like dominating the uppermost regions of the exosphere? So wouldn't you expect to see a lot of hydrogen the higher up you go?
Yeah, that's a very good point. This is where the Lyman alpha is absorbed. This is the altitude where it's mainly absorbed. And I think the hydrogen that you are referring to is here, for example, the red line. It becomes more and more important while you move to higher altitude, right? Am I understanding your question correctly?
Yes. Yeah, exactly.
Okay.
Okay, that makes more sense. So what we were looking at before is the absorption of Lyman alpha, and that is happening like at and below 100 kilometers, but the density is increasing the higher up you go.
Yes.
Okay, thank you.
Okay, so if no more question about the thermosphere, I'm gonna move to the ionosphere part. Okay, so the ionosphere, as I just mentioned, the ionosphere refers to the plasma, population in the same altitude range as the thermosphere. And then the different layers are based on the number density changes. And so whenever you see a local peak, you define that as a layer of the ionosphere. The two most popular layers or most frequently seen are the F region around 200-300 kilometers and the E region around 100 to like 150 kilometers. And those two are the most often seen. Sometimes you will see a D layer that's happening, around 90 or 80 kilometers, and due to very high energy particles or X-ray range of solar radiation. But the D region here is not as often, occurs not as often as the E and F layers. Okay, so if you still remember the charts that I mentioned to you about the relative density of electron or plasma and then the neutrals. So in the E region, their densities are 5 order of magnitude different. In the F region, about 2 or 3, right? So that directly controls the most important dynamic process that will occur in the ionosphere. So for example, in the E region, because of the very frequent collisions with the neutrals in the surrounding regions, this is the layer that's mainly controlled by chemical process, because things happen so fast that there is not enough time for other transport or diffusion kind of dynamic process to occur. But when you move to higher altitudes, when the neutral density decreases very quickly, and the other dynamic process like transport and diffusion can starts to compete with the chemical process in the same region. And so in those regions, their dynamics would be affected by all of those processes. Okay, so there are some important parameters that you will often see when you start to read the literature about the ionosphere. I'm just listing a couple of them here. So because the importance of the F region, people give different names to the peak height or peak density of this F region. For example, the peak height is called the HMF2, and then the peak density is NMF2. Okay, so that's what people often use to indicate the important physical parameters that's associated with the F region. Another parameters that I want to mention is called total electron content. And some of you here probably have done some research or learned about this. It is just the integration of the electron density, within a column of unit area from your receiver and all the way into the transmitter. So very often we have ground-based, GPS or GNSS receivers, and then the GNSS satellite flying somewhere around like 20,000 kilometers, right? So then the electron density that's calculated between the satellite and the ground receiver gives us the total electron content. That is a very useful parameter that we often use to characterize the ionosphere plasma content and how it changes as a function of location and then time. Because nowadays we have thousands of receivers available over the globe, and so this really comes as a very handy parameters, for us to do ionosphere research. So looking at this chart here, I mentioned the different layers, but then now if you look at the most abundant chemical species in those layers, you will see that in the F region, it is many O+, but in the E region, it's many molecular species, right? And so actually in the E region, the most important ones are the O2+ and NO+. You might be very surprised why N2+ is not the most abundant one. And then in the next couple of slides, I'm going to talk about the chemical reactions, the major chemical reactions that is happening in the E and F regions, and that will help you understand, why the O2 or NO+ or O2+ are the most important ones in those two layers. Before we talk about the chemical reactions, I want to detour a little bit and talk about one of the applications of ionosphere, right? So we all heard about radio communications, and then the radio communications enable us to communicate with someone that's far away from us. We use the ionosphere as our reflection point, for short or long distance communication. For example, if you have a transmitter located here and sending out a radio wave, and that wave will be reflected at an altitude where the plasma frequency matches with this wave frequency that you send out, right? And after that point, then the electromagnetic wave will start to reflect it backwards and then finally reach the receiver location. So depending on how far your receiver is from you, and you will choose the different radio wave frequencies and then utilize the different reflection point to reach the receiver. But sometimes if you choose an electromagnetic wave that is too high of a frequency that you can find nowhere to reflect that wave, then you won't be able to communicate with the receiver on the surface here. So this one highlights one of the reasons it is so important for us to be able to forecast the ionosphere conditions, right? You want to know what would be the maximum frequency that can be used for your communication. So there is a very easy and handy equation that people often use is if you know the ionosphere density, especially the altitude where you want your wave to be reflected, you can calculate what is this critical frequency, right? basically the maximum frequency that you can use for your high frequency wave communication. So this is one application that people often use for taking advantage of the ionosphere, is for this long distance radio communication. Most of those electromagnetic waves would reflect in the F region, because that is the highest, the region with the highest density that determines the maximum frequency that you can use. The ionosphere can be probed by many different instruments. Some of my favorite are like incoherent scatter radars or ionosondes. So this chart here shows a long-term record of the E region and F region critical frequency that is measured by a ground-based ionosonde. And so you can see that the solar minimum, solar maximum conditions are also marked here. So I want everybody to spend a minute to look at those two curves and see what type of trends you can identify, and what does that tell you, or can you guess where the receiver is?
So go ahead and type in the chat or unmute.
Yeah, if you can raise your hand, I think Mark, you can
Yep,
unmute
I can
them, or they can unmute themselves. Yeah.
Yep.
Shasha, can you remind us of the question?
Okay, so the first question is what type of trend you can identify just based on this chart. And then the second question is more tricky one, is whether you can guess the location of the receiver. Like in one hemisphere. Be more specific. Yeah. Oh, I saw a hand. Yeah. Go ahead.
Well, there's like a solar cycle variation, especially in the F region, with more it's higher in near solar maximum. And I also noticed that it's like a double peak for each of the bumps.
Yeah, great. Yeah, so we see higher F region frequency during solar maximum and lower frequency during solar minimum. If you still remember the equation that I showed in the previous slide, right, there is a direct relation between the frequency and then the density. So this one actually tells you how the F region density changes according to the solar cycle, right? Okay.
And in the chat, Stephen suggested seasonal variations.
Yes, seasonal variations. Yes, perfect. We can see them in both the F region and here in the E region as well. Yeah. So, for example, in the E region, we see higher frequency or higher density during the northern hemisphere winter, right?
So Sanjay's inferring that since the higher densities are in December, January, that the receivers in the southern hemisphere.
Yes, perfect. Yeah, that is the second more trickier question. Yeah. So yeah, you can see, based on a simple chart, like a time series of those critical frequencies that we observed in the E and F region, we can find out a lot of information about the ionosphere, how those two layers, change as a function of season and as a function of solar cycle, right? Okay, so let's move on to the next one. Okay, so next let's talk about the ionosphere composition. This gets a lot more interesting. So here you can see that there are many curves joining this chart. This one here that my mouse is highlighting, this is the total electron density, okay? And then for the other curves, when there is a chemical species that's labeled next by, that means the density for that specific species. Okay, so let's start from the bottom, the E region here. It's a little bit hard to, tell which one is which. So this one here is the O2 plus, and then this one here is the NO plus. Okay, and as I mentioned, the N2 plus is not the most important molecular species in the ionosphere in those regions. And so you can see that the density of the N2 plus is about 1 to 2 order of magnitude smaller than those two. And you might be very surprised. Why, right? Because the N2 is the most abundant molecular species, like in the E region, especially in the lower part of the E region. And so then we need to look at the chemical reactions. Okay, so in the E region, the two most abundant neutral species, and well, the mother of the ionosphere, is N2 and O2. The solar photon ionize those two molecular species and then generate N2 plus and O2 plus. But then the N2 plus will charge exchange with the ambient atomic oxygen very quickly. So that generates this NO plus and atomic nitrogen here. This is a very fast reaction. So once the N2 plus is generated through ionization, it will very quickly charge exchange and become into NO plus. So that is why you see the NO plus is one of the most important plasma species in the E region. It's because of this chemical reaction is very fast. Now, the N2 plus, once generated, they can also recombine with the ambient electron and then goes back to the 2 atomic nitrogen, right? Or the NO plus that's generated in the first equation here can recombine with the ambient electrons and become atomic N and O. So why we still see an existence of the NO plus and then N2 plus in those layers? One of the reasons is that this second chemical reaction here is much slower than the first charge exchange reaction. This one is about 5 order of magnitude smaller or slower than the first one. So vast majority of that N2 plus, once generated, become the NO plus. Okay. So similarly, the O2 plus can be ionized and then becomes the O2 plus. And the major loss process for the O2 plus is again the recombination. So this one is at a similar speed as this one, the second one here. They are much slower than charge exchange. So we still see a lot of N2 plus in the final, plasma density there. So if I go back to the previous slides, you see the N2 and the O2 are the most important ones in the E region and sometimes to the lower part of the F region. And those chemical reactions and how fast they are basically tells you why they are the most important ones there. Although we have a lot of neutral N2, but once the N2 plus is generated, they get converted to the other species so quickly. So they're not the most important ones in the region. Okay, so if we go to the F region, the most abundant neutral species is atomic oxygen, and that is because of photodissociation we mentioned earlier. The incoming solar photon can directly ionize the atomic oxygen and then generate O+. The O+, the loss process for it is also a 2-step process. The first step is again charge exchange, So O plus will react with the neutral N2 in the surrounding region and then generate again NO plus and N. And the second reaction is NO plus recombine with E or the electrons and then becomes the atomic species again. So again, this charge exchange is very efficient. One of the reasons is that the neutral N2 is, there are a lot of neutral N2 in the surrounding region. Remember, in the F region, the neutrals are still 2 or 3 order of magnitude higher than the O plus or than the plasma, right? And so there are a lot of N2 to be used for the reaction. And that's why once the O2 plus is generated, they will be converted to NO plus and then recombine. The NO plus later recombine with electrons. So these 3 reactions that happening in the F region actually tells us why the O over N2 ratio is so important. This is because the production of the F region plasma depending on the atomic oxygen's density. But then the loss process, here is mainly determined by the abundance of the molecular N2 there. So you will see that in the research community, people often talking about the neutral O to N2. This ratio is very important in determining the F region dynamics. And these 3 equations tell you why. Okay, so production is controlled by atomic oxygen concentration, but then the loss process is mainly controlled by the neutral molecular N2 density. Okay, so I think this there is a lot of information on this slide, so maybe we can take a break right now and then continue the lecture at 11 here. Yeah. This is from or?
There's a question on slide 14, the one you were, and I think Pauline had pointed out that there seemed to be a double peak. The question is from Florian, why? Well, yeah, so slide 14, that one, in the F region peak density, or
Yeah, so in the later part of this lecture, we will talk about seasonal variations. So if you look at those 2 peaks here, now it's hard to see, but I think one is somewhere close to like the January, right? And then the other one is now it seems hard to line them up. Maybe we can draw.
yeah, they're quasi regularly spaced.
Yeah, so the frequency seems to be not fixed, not always like that. Yeah, but let me try to see whether we can identify that. Is this a straight line? Looks to me it is. Okay, so this is like closer to the end of the year, and then the other one is like the beginning of the year, right? Yeah. I don't have a conclusive, explanation for this. I think this is related with actually the seasonal O over N2 ratio changes related with thermospheric wind. And we will see later that the seasonal wind variation will change the O over N2 ratio, and that will change the F region density. So you will see that later towards the end of this lecture. But that's a very good observation. Yeah. I think the interesting part is it's not always like that. And sometimes it happens a little bit earlier or later. Yeah.
Great. And so, Nick, do you have suggestions for coming back at the top of the hour, or
I think the top of the hour looks like a good time. It's 8 minutes away.
So there are a few questions and suggestions, but we can hold those as well. So let's take a break until the top of the hour.
Okay.
Can I get a show of faces and our thumbs ups just to get a sense of a quorum? And then I guess the most important person here is none of us except for Sasha. So I guess she'll start off. And then I think there's a couple of questions for Hasna, hopefully recovered from your birthday celebrations. I think Sasha described him as the mother of the ionosphere. It's essentially that's the main neutral species. So as mentioned, whatever the dominant neutral atmospheric species often plays a big role in what's the dominant ion. But what's interesting for the Earth, we think N2, which is the dominant neutral molecule, would be the dominant ion, but it's not. It's not even O2, and it's because of a lot of the photochemistry. And I think Matt had answered Miguel. So we're ready whenever you are, Sasha.
Yeah, and I want to thank Matt to point out I misspoke one thing when I was talking about the chemical reaction here. So I meant to say that the charge exchange, those reactions, this one and then this one, is the rate control one. And the second step, when the molecular species recombine with the electron, this is actually much faster than the first one, because the first step, the charge exchange, is slower. So this is the rate control one. The whole loss process is basically determined by this first charge exchange reaction. And then I want to say the molecular species like the N plus and O plus, when they recombine with the electron, that is a very slow process. So thank you, Matt, to point that out. Okay, so let's see. Is there any other question about the chemical reactions before we move on?
There are a couple that popped in. One about the D region, how it remains constant. I don't know if Pabito, you want to unmute and ask that? I'm not sure if that's in terms of density. I think so.
Okay, so the D region, the chemical reactions there is really complicated. There are a lot of them. And the reason that we did not include the D region here is first, it does not occur all the time, and it needs very energetic sort of photons or energetic particles. And the second one is because of the neutral densities, there is so large. So the D region chemical reactions occur very fast. And whenever you have some significant plasma populations created there, once you cut off the source, they almost disappear immediately. So very fast.
And then the last question, Raphael, was what essentially the rule of thumb on O to N2 ratio. If it's a big one, what should you think? And if it's small, what should you think? Or what does it imply if you have a big O to N2 ratio?
Yeah, so if you have a higher O over N2 ratio, then you have larger production rate than your loss rate. So you expect a higher NMF2 and then TEC. Yeah. So, and then if you have a lower ratio, then vice versa. Yeah.
Great, thank you.
Okay. Okay, perfect. Let's keep going. Oh, okay. So I put this slides here just to remind you about, the abundance of atomic oxygen and molecular nitrogen, their densities. So you can see in the F region, which is above like 200 kilometers most of the time, the oxygen density is higher than the N2 there, just because it's lighter, so it decreases slower. So this is basically for your reference. Okay, so now we learned about, the chemical reactions and the rate are different at different layers. And so it is important to think about, if I ionize the ionosphere in a particular location, for example, I generate the F region, I generate the E region, right? And now what will happen if I turn off the source process or turn off the photoionization? So in the E region, because the chemical reactions are so fast, the E region densities decreases very quickly. As you can see in the next hour, the E region is about 2 orders of magnitude smaller, so it basically disappeared, right? But the F region, it slowly decreases. As you can see in the next several hours, you can still see a pretty prominent F region density. So this also tells you what may happen after the dusk terminator, right? So after the dusk terminator, the E regions will disappear very quickly, but the F region has a longer lifetime. It usually can survive almost to the midnight, but then the density will become very insignificant just before the sunrise. So this is a really nice controlled experiment by numerical simulation, tells you how important the different loss process that's happening in different layers will do to the ionosphere density. Okay, so we were talking about seasonal variations, and the next thing that I want to discuss is how the seasonal variation of the O over N2 ratio gives us the large scale seasonal variation of the density that you will see later. So we know that during equinox, the sun shines near the equator, and then for solstices, the sun would move to either the northern or the southern hemisphere. During those solstice time, that means that we have differential heating in the two hemispheres. This chart here shows that the summer, this is the summer hemisphere, right? And the summer hemisphere gets more solar radiations, and the solar radiation is mainly absorbed between 100 and 200 kilometer, that layer, right? Still remember the solar photo absorption? So once you have the solar heating that's stronger in the summer hemisphere, then more heating happens in the lower thermosphere. And then you generate a vertical thermospheric wind, and that wind will bring the rich, molecular rich, like N2 rich, air to higher altitude, right? And then in the higher altitude, it will blow from the summer hemisphere across the equator and all the way to the winter hemisphere. So this blue circles here is the solar radiation controlled seasonal, large-scale seasonal thermospheric wind circulation that will happen. Because the rich N2 air was brought to higher altitude in the summer hemisphere, and then when the wind carries this reduce the O over N2 ratio air to the northern hemisphere, So in the summer hemisphere, your O over N2 is reduced. But in the northern hemisphere, you will gradually see your O over N2 ratio is actually higher. And why is that? It is, again, because the N2 is heavier than O. So during the transport process, the N2 will gradually settle down, but you can have more atomic oxygen that is carried over to the other hemisphere. So the large-scale thermospheric wind circulation in the background here will also introduce a hemispheric asymmetry in the O over N2 ratio. So this blue line here basically tells you what the O over N2 concentration will be as a consequence of this large-scale thermospheric wind circulation, right? So this was earlier proposed by Rischbest, but nowadays we do have observations that can demonstrate this is indeed happening. So what I'm showing you here is the O over N2 ratio that's measured by a NASA satellite. It's a GUVI instrument on board of the timed satellite. And so this one tells us the global O over N2 ratio distribution. The satellite, it will take the satellite basically a day to go over all the longitudinal regions. And so what you are looking at here is not a snapshot. You can view this as like one map per day, type of map. So here you can see this is January 18th, 2016, right? So it is winter in the northern hemisphere. But if you look at the O over N2 concentration, we actually see higher O over N2 concentration in the northern hemisphere, and then the lower concentration in the southern hemisphere. So this is again a direct observation that's demonstrating that large-scale thermospheric wind circulation generated by differential heating is indeed true, and we can see them clearly in those O over N2 ratio maps. Okay. So next, I want to briefly talk about the plasma thermal structure. Actually, in those charts, not just the plasma temperatures are showing, but also the neutral temperatures are shown. So first, the left panel shows on the day side, I think it's the afternoon sector, and then the right panel here shows on the night side, around 2 local times. So comparing those two panels, I think there is one thing that you can see very clearly is that the electron temperature is the highest one among the three, and the neutral temperature is the lowest one. The ions temperature is almost always, in between those two. And the reason is that in the lower altitude, the ion and neutral collisions are very efficient. So the ion temperature is always mimicking what the neutral temperature would be. And at higher altitude, the ion temperature is strongly modulated by the electron temperature through Coulomb collisions, and that is between the electron and the ions. And so the ion temperature can increase at higher altitude. Then you may wonder, what controls the electron temperature? Electron temperature is a very complicated process. We can talk about the two most important things. The first thing is the one that's setting up this gradient. You can see the higher temperature at higher altitudes, and in general, lower temperature at lower altitude. And this tells you there is a heating source at the top of the ionosphere, right? So that is actually the heat flux coming from the magnetosphere or the plasmasphere. In these numerical simulations, they have to set up this heating or heat flux at the heating source at the top in order to produce this profile that can be comparable or with observations. And so the heat flux is actually one of the most difficult parameters that to measure. So in a lot of cases, people just use it as a tuning parameters to adjust the heat flux, the amount of heat flux, and to try to match the temperature curve with observations. In the later lecture, I think Matt will talk about simulations. Maybe he will mention this part. But yeah, in general, heat flux is the one that we need in order to set up this gradient. Now, comparing the day side and the night side, you will see on the day side there is like a kink, right? This kink here around 200 kilometers and indicates the local heating. And this local heating is due to the photoelectrons that's generated by that ionization process we were looking at. And the photoelectrons, once they are generated, they're actually a lot more energetic than their surrounding, like the very cold ionosphere electrons themselves. And so the photoelectrons will collide with those thermal background electrons and then gradually transfer their energy to those thermal electrons in the background. So that is how the background gets heated on the day side. So we only see this type of local heating on the day side. On the night side, because we turned off the photoionization, so we don't see that local kink here. I saw there are several maybe questions in the chat.
I think Matt was able to answer it. There was a technical one on the GUVI imaging, had a hole in the South Atlantic anomaly.
Yes, exactly. Yeah. So the data there is not reliable. We usually block it. Yeah. Okay. Okay. So after understanding that general temperature trend for ions and electrons, we can look at some real measurements. And this is from the Millstone Hill Incoherent Scatter Radar. And it is one of the radars, one of the very few radars actually located in the mid-latitude to subaurora region. And then the pictures that you are looking at actually trace back all the way to the 1970s. Those pictures come from the Shankan Nagy book. And so if you're wondering where those pictures are from, those are from that book. So this one shows us the typical diurnal variations of those important parameters, the number density, the electron, and then the ion temperature. So similar to what we have looked at before, on the day side, once we have the photoionization, this is the region where we see the largest density in the ionosphere, both in this is mainly in the F region. The E region was not plotted here, but there should be a E region enhancement here as well. When you move to the night side after the terminator, you'll start to see the density decrease. And so the most or the fastest reaction happens in the E region, so they disappear very quickly, and the F region slowly decreases and reaches the minimum just before sunrise. That's so because on the night side, there is no other energy source for you to ionize. The Millstone Hill is in the mid-latitude subaurora zone. Only during very strong geomagnetic storms that we can have additional ionization that's due to particle precipitation coming to this altitude. The picture here is a very typical choir day, so you don't see that. It is just the very simple diurnal variation. Now, if you look at the temperature is actually interesting. You see that the highest temperature here is also on the day side, right? And again, that's where the heating is from, solar radiation, and then the lowest temperature that happens just before sunrise. And not surprising, for the ion temperature, the trend is similar to the electron. It is just in terms of magnitude, it is always smaller than the electron temperatures. Okay. So we were looking at the seasonal anomaly, and I mentioned very briefly in the earlier of the lecture that the seasonal anomaly is mainly controlled by the O/N2 ratio. Okay, so we looked at one example from GUI that in the winter hemisphere we can actually have higher O/N2 ratio, and that is due to the large scale thermospheric wind circulation. So the direct consequence of that thermosphere composition change or hemispheric asymmetry is reflected in the ionosphere density. So because of the O/N2 ratio is higher in the winter hemisphere, we can actually have a higher O plus density in the winter hemisphere. And that is surprising because we thought, the sun is shining directly in the summer hemisphere, right? Maybe we can get more ionization there. But the fact is that the mother thermosphere changed. And so the ionosphere density, the O plus, is actually also affected by the O/N2 ratio change. Now we have higher density in the winter, like the picture is showing here. Let's see. The temperature is the left panel and the electron density is the right panel. Winter is the dashed curve, and so you can see the winter hemisphere, the density is actually higher than the summer one. And this is directly due to that O/N2 ratio asymmetry. So this one is called the winter anomaly. Now, if you look at the temperature shows exactly reversed trend. In the winter hemisphere, where we have higher density, we actually have lower electron temperature, right? But then the summer temperature is higher. So this is because the solar radiation that's in the winter hemisphere now needs to be shared by many more electrons there, right? Because we have a higher density. And so each one of them gets less share of the energy. That's why their temperature is lower. And so this is the inverse relationship that you will hear people talking about between the electron density and then the electron temperature. We see this in many structures in the ionosphere. For example, some of you might heard about the storming enhanced density, right? So that is a prominent density structure during storm time in the ionosphere. And we also observed this type of inverse relationship between the electron temperature and the density. Okay, so after looking at that seasonal variations, I want to look at the solar cycle variations at mid-latitude. One thing that you might wonder is why I always show mid-latitude, and the reason is that the mid-latitude is considered as a region that's maybe we have less anomalies and definitely less affected by geomagnetic activities. And so the mid-latitude ionosphere is often used as a region. We think it's a safe region, away from the high latitude dynamics, and maybe can be used as a good representative for the average ionosphere condition. But as you can see, it's not always like that, right? But still better than high latitude. So that's why I'm showing a lot of the mid-latitude pictures. So after understanding that seasonal variation, let's look at the solar cycle variation. We know at solar max, the solar EUV radiation is much higher than that during solar minimum, right? And also the thermosphere temperature is higher. So you have more energies and you have more thermosphere oxygen density waiting there to be ionized. That means for solar maximum, we can have higher electron concentrations in the F region. And again, because we have higher densities and the electron temperature might be actually lower than the solar mean. So again, if you look at here, the solar max, you have higher density, but then the electron temperatures can be actually lower than that during solar minimum. This is again where that inverse relationship shows up, right? Okay, so in the chart here, you can see there are two curves. One is a solid curve and the other one is a dashed one. The solid one is the measurement by the Millstone Hill incoherent scatter radar, and then the dashed one is actually based on numerical simulation. It's a calculated one. The good agreement here, assures us that we think the physics behind that, we understand it, and then incorporated that into the numerical simulation. So that's a good sign. The simulation agrees with the observation. Okay, so this is the end of my first lecture where I want to talk about the ionosphere and thermosphere basics. I think this is a good time to spend a couple of minutes taking questions before we move on to the other one.
Yep, and we have about a half hour for the next one. Is that what you were planning?
Yeah, the next one I have fewer slides.
Okay.
Yeah.
I
Maybe I will change my slide while waiting to see whether there are questions.
Yeah, go ahead and raise your hand or continue to type into chat. Great, so it looks like we're ready to jump in to the dynamics.
Okay. Okay. So next I'm gonna move to the dynamics. And for the dynamics, I wanna talk about the most important structures that's in the equatorial region and in the high latitude region. Okay, so we start with the equatorial region. Before that, let's look at this picture. I think some of you probably looked at this before, right, Mark? I think you give an introduction about this. Yeah. Okay.
Yep.
Okay. So as we see the video, and earlier you heard from Mark that the equatorial ionization anomaly is probably the largest scale structure that's happening in the ionosphere. And the formation of the equatorial ionization anomaly is a direct consequence of the ion neutral coupling that's happening, in the E and the lower F region there. Okay, so it was discovered by Edward Appleton back in the 40s and 50s, actually back in the 40s. One of the few scientists in our field actually win Nobel Prize, right? So why is there such an anomaly? And then actually an anomaly that happens on a daily basis. In order to understand that, we need to understand a process called E-region dynamo. So the E-region dynamo tells us the dynamo that happens, of course, in the E-region, and it is the solar-driven wind, and then the thermospheric wind interaction with the plasmas in that layer. Okay, so let's first look at the wind circulations in the E-region. Let's see. So the top one here shows the height integrated velocity between 100 and 300 kilometers, and this is the neutrals. Okay, so the neutral wind. So for the neutral wind, you can see it is mainly controlled by the solar heating. The divergent wind happens in the region in the afternoon, and this is the hottest region in the thermosphere. So the neutrals would expand and generate divergent wind. So you see that the wind blows from the afternoon sector to the morning sector near the equator region, and then on the night side is opposite, right? Oops. So the panel B here shows the Peterson dynamo current that is driven by the wind. Okay, so the Peterson current, you can see it's also kind of divergent from like the dusk sector here, and then we have the convergent currents blowing on the day side. The panel C shows the Hall dynamo current, and then similarly you can see that the Hall dynamo current gives us a roughly counterclockwise structures in the northern hemisphere and then clockwise structures in the southern hemisphere. So the dynamo current, that's either both the Peterson and the Hall current, they diverge from around the sunset sector at the equator, and that is the region where the negative charges that can be accumulated. Then why is that? That is because the ion neutral collision is a lot more efficient in those regions, and so the wind, when they diverge in the dusk sector, they can blow the ions. You can think about they can blow the ion or carry the ions with them, so left the electrons in that region. And so we can have the negative charge that's accumulated in those late afternoon and then dusk sector. But then the wind can carry the positive charge ions to the morning sector. Okay, so this is one way of creating a charge separation in the system. Another way of looking at that, a lot more simpler, is that again we have negatively charged particles accumulating in the dusk sector, and then positive charged particles accumulating in the dawn sector, right? So this charge separation gives you an eastward electric field on the day side, and then westward electric field on the night side. This eastward electric field on the day side is perpendicular to the magnetic field near the equator, and this will gives you a E-cross speed drift that can move plasma to higher altitude. So this is a multi-step process. The first one is that divergent wind here near the dusk sector carries the positive charge particles away, right? That gives you the net negative charge particles or electrons there. And we have positive charge particles in region where the winds converge. So once you have this charge separation, you create eastward electric field on the day side and then westward on the night side. Okay? So this one, the text here is a little fuzzy, so please bear with me. The previous two slides basically explains the step 1 here, charge accumulation and separation. And step 2 is that we can have the eastward electric field that's due to this charge separation. This eastward electric field is perpendicular to the northward magnetic field there. And so E cross B drift, if you use your right hand, E is the direction where your thumb is pointing, and then B is where your 4 other fingers pointing. So E cross B gives you an upward velocity, right? Or another way of looking at that is, if I go back to the previous slide, here, E cross B in this geometry will give you a velocity that's going this way, right? So to higher altitudes. Yeah. So in this way, the plasma that's generated here in the E and the lower F region can be carried to higher altitudes in a region where the plasma will start to feel the other forces like gravitational force and then pressure gradient force. So then they will start to diffuse along the magnetic field to both hemispheres. So if you look at this black and dashed curve here, this looks like a fountain, right? You have the plasmas moving to higher altitude here near the equator, and then they diffuse along the field to low latitude regions in both hemispheres. This fountain effect will generate that equatorial ionization anomalies because we moved more plasma to those low latitude regions and from the equator. So creating that low density trough near the equator and then the high density in the two crest or EIA crest region. Okay, is there any question about the EIA before we move to, I think, the high latitude region?
There's nothing in the chat.
Okay.
Oh, no, yes, there is. Why is it mainly at the E layer, or why is the E region dynamo play a big role?
Okay, that's a very good question. So in the F region, when the neutral densities decrease, the collisions between the ions and then the neutrals become less efficient. And E region is also the region where we consider the ions and electron actually move in the same direction. So you can think about it in that way that the wind there is less efficient in creating charge separation. Okay, let's keep going. So in the earlier slide,
Before there is one question, Hasna, if you want to unmute.
Yes. Hello, Shasha. Thank you for your presentation. I have a question in this slide. Actually, I wonder if I understand right or wrong. Sorry, the last slide. Yes.
this one, yeah.
Yes. The mechanism of the dynamics in E region and F region. There is a magnetic field and the wind, neutral wind upward to the F region. These are the two mechanisms to make these dynamics, or there is another things in these regions.
You mean the neutral wind here in the F region?
I mean, of these dynamics is the magnetic field and electric field dynamics, in addition to the neutral wind motion.
I think what's the physical process that gives rise to the anomaly? Is it the electrodynamics or is it the neutral winds?
Oh, I think it's a combination, and then they have different roles in different layers. So in the E region, this is the region where the neutral wind can efficiently create the charge separation. You can see the charge separation that's highlighted here in this E region, down here. And then the E cross B drift is more important in the F region, where the collisions between the plasma and the neutrons become less efficient. And in a lot of cases, we actually just ignore the collisions in the F region. And so the plasmas there are directly controlled by the electromagnetic force there.
I'm sorry, why we usually ignore the collisions in F region?
It's because the neutral density decreases very quickly, and so when in the F region, the collisions between the ions and neutrals and electrons and neutrals are comparable. So that's the layer where the wind cannot separate ions and electrons. So you can consider the ions and electrons move in the same direction, and the direction is controlled by the ambient electric field and magnetic fields.
So it's difficult to separate it and calculate these calculations, right?
Yeah, in reality, there is like no magic boundary, saying that above that, we completely ignore the collisions. But this could be, this is a simplified cartoon. In reality, the boundaries between these two processes are not as clear as those cartoons.
Okay, and these phenomena occur in the day side, or during the day, I mean, right?
Yeah, so this is a process that occur on the day side, because on the day side we have the solar heating produce the E region wind that creating this charge separation. On the night side, as you can see, actually the electric field here is westward, right? And so if again you use your E cross B, you will see that will give you actually a descending force, right? So it's opposite to what we can get on the day side. So the EIAs are expected to gradually disappear on the night side, both due to that E cross B drift that's changed, reversed its direction, and also due to the disappearance of the solar-driven neutral wind, in the E region. Yeah. So you're right. This is a process that's mainly happening on the day side.
Thank you.
Okay. If no other questions, I'm gonna move to the next topic. So this is we will look at the high latitude. The high latitude region is a lot more dynamic, and the reason is that the high latitude is directly mapping into the Earth's magnetosphere and even the solar wind, right? And the conditions in the magnetosphere and solar wind will directly affect the high latitude in many different ways, like high latitude convections, or by field line currents and particle precipitations. So the equator and low latitude dynamics are mainly controlled by the solar EUV, or solar radiation, but the high latitude dynamics is highly controlled by the solar wind forcing. We spend a lot of time talking about how the solar radiation create photoabsorption or ionization in the ionosphere and thermosphere system. The other very important energy source is the solar wind. The solar wind is carried by charged particles all the way extending from the solar atmosphere into the near space environment. Some of the critical parameters that we often consider in the solar wind are the charged particles density and their velocity, and the magnetic field that's carried by those plasmas. In particular, there is a component of that magnetic field that is the north and south. If you think about north and south direction, that is a very important component that controls the physical process, how efficient the solar wind energies can enter the Earth's magnetosphere. Okay, here is a simulation from our University of Michigan Space Weather Modeling Framework, and it shows you the structures in the solar wind dynamically affecting the Earth's magnetosphere. So you are looking at the magnetosphere from the side. The sun is here, right? Here is oops, it disappeared. Let me show it again. Okay. So it is the plasma pressure, and the white lines is the magnetic fields. Why is it changing? So the point that I want to make here is the geospace system is directly controlled by the solar wind, the shape of the magnetosphere. Okay, let me keep going. Because the solar wind is highly variable, sometimes we will have those large scale eruptive structures coming from the sun, such as the corona mass ejection, or we might have what we call the co-rotating interaction region, carrying highly varying interplanetary magnetic field into our geospace system. So, and create the geomagnetic storms. Geomagnetic storms is the largest geomagnetic disturbances in our system. And during storms, both the equatorial system and then the high latitude system that's highlighted here will expand. And that will create some very interesting structures in the ionosphere, such as storm enhanced density or plasma plume that you have heard other people talking about. And there are impulsive heating in the high latitude region drive the traveling atmosphere disturbances or traveling ionosphere disturbances that's moving from high to low latitude region. So those structures occur during strong driven conditions where we have a lot of energy coming from the solar wind that's deposited into the high latitude region. Now storm, I mentioned the storm. Geomagnetic storm is the largest disturbance and can create global scale changes and last for a couple of days. The smaller disturbance that people often talking about is called a substorm, but be very careful. Substorm doesn't mean small storm. It's just when it was first discovered, people think it's a small storm, but then later realized those two are actually very different things. So substorm is more local, and many happens in the night side high latitude regions where you can see very sudden brightening and expansion in the aurora zone. It often lasts for like just a couple of hours, and it can happen during all the seasons, even during solar minimum. We can still have substorm. It's just the frequency of substorms might be less than storm for during the substorms may less occur during solar minimum than during solar maximum. Just to give you some idea about how often substorms occur, we can have roughly like 1,000 to 2,000 substorms, for any year during a solar cycle. But the storms, this one is highly controlled by solar cycle, and we may not get any large storms during a solar minimum, right? So the other one is called a shock compression. Is that we have very fast solar wind structures that's coming from the sun and towards the earth, and so it can create those sudden compressions of the geospace. This is a transient but still global disturbance, and you can see it only lasts for several minutes. So those are the three geomagnetic disturbances, the major three. I'm not going to talk about the 2 and 3, so I will focus only on storm very briefly here. So the storms are defined by what we typically call the strength or the magnitude of the ring current in the magnetosphere. I'm running out of time, so I'll be very brief. So in the magnetosphere, typically around 4 to 6 Earth radii, a current can form during geomagnetic storm time, and it's westward. And so if you use your right hand, you will see the westward current will give you a negative perturbation on the surface, right? And so people have been using the magnitude of that negative perturbation to infer the strength of the ring current and then the strength of the storm. So that's often how we define the storm. The parameters that people use is called the disturbance storm time index, or DST. Some of you may also heard about the higher resolution version, and that is called the CMH, right? So both of them measuring the negative perturbation that's generated by that westward ring current. Okay, you can further classify storms based on the DST. Okay, so there can be hundreds or thousands of gigawatts of energy that's dumped into the ionosphere and the thermosphere system. Majority of that energy comes in as electromagnetic energy or Poynting flux. You can see it's roughly 80%, and 20% coming in as energetical particle precipitations. In both cases, those particle precipitation and electromagnetic energy goes to heat, ionize the thermosphere and create more charged particles. They can also create like auroras or air glow. But the ultimate energy sink is the thermosphere. Even though you give energy to the ionosphere, but because the ionosphere density is much lower than the thermosphere, and they collide very efficiently with the thermosphere, so effectively the ionosphere acts only as a bridge, to transfer the energy received from the magnetosphere and all the way to the thermosphere. Okay, so what should I do, Mark? Since we're running out of time, should I just stop here?
You can go for a few more minutes. We have the office hours, and if we take a few minutes in, but if this is a natural break point, that's fine as well.
Yeah, I think it's better for me to stop here because I was planning to talk about like highlight to convection and new wind pattern, but that will take another probably 15 minutes. So okay. Yeah, I'll stop here.
And we had from the magnetospheric perspective a lot of the high latitude polar cap convection.
Oh, great! Oh, great!
So from yesterday, so great. So open it up. Please feel free to raise your hand or type things in the chat box, and hopefully start seeing these connections. Even though we're magnetospheres and ionospheres, obviously highly coupled. A quick question on this partition of energy from particle precipitation and electromagnetic energy flux. In the auroral zone, what would you, or is your thought process, is that more equal partition of auroral precipitating particles plus field line currents and Poynting flux going in there. And this 80% or greater than 80% is more of a global average, or not only near the auroral zone.
Yeah, this is actually many near the aurora zone because
Okay.
this total energy, incoming energy, is considered coming from the magnetosphere. And then during the disturbance time, I think the high latitude aurora zone directly maps to basically the whole magnetosphere, right? So that's a region where those energies are deposited. Yeah.
Great. Yeah, and then we're going to have a discussion tomorrow on the decadal survey, and you can, one of the ideas of a decadal survey is to help to define new missions. And the Geospace Dynamics Constellation is a mission that had been recommended from the last one, but they actually did not prioritize measuring Poynting flux as a key parameter, which is like, what? And so both Shasha and I are on investigations trying to measure that.
Yeah, I was very surprised to see that in the AO.
Yeah.
I think the previous study, especially like this one coming from Ganglu, who is an expert in my coupling, had clearly indicated that majority, you can see 80% of the energy coming as Poynting flux. So being able to measure the magnetic perturbation and then to measure both the DC and AC Poynting flux is extremely important for the success of the GDC mission. Yeah.
So they do have one of the instruments in phase A is a magnetometer, right? So I think that
That's
was
right.
one of the things that I found weird was that you know, there wasn't a requirement in the STDT for a magnetometer, which I thought was bizarre. But anyway.
Yeah, that was the point. So decadal surveys are very important, and science definition teams are very important. But there is a question from Miguel on, does the fountain effect have any composition mass dependencies, or do they lift everything up?
That's a very good point. So let me move. I'm going the wrong way. Oh no. Yeah, the mass is actually not listed here, but as you can imagine, the E cross B force itself is depending on just on the ambient E and B fields. So all the particles experience the same E cross B force, but then the diffusion and then gravitational force, those are depending on the mass, right? So the different species indeed experience the different combination of the forces. So I wouldn't imagine that the heavier ions will have a more difficult time of getting to, you know, the highest altitude. So the lighter ones, especially the most abundant one, the O+, should be the dominant one that can reach the highest altitude here. But that's a very good question. I actually have not really studied on the different fountain effect based on their species. But so those are my thoughts at this point, you know, in real time.
I would speculate that the effect on the neutrals might be kind of small because the forcing is through the plasma, and in the F region, it's you know, a factor of 1,000 less. Yeah.
I saw the question is about the charged particles in the different.
Oh, okay. I misread that. Yeah, sorry.
Well, in fact, sorry, it was both of them. If neutrals and also ions were carried out, but also the change in the neutrals may also impact the population, I guess. So I don't know.
Yeah, my response was purely speculative. Actually, there could very well be some other process that makes this important.
Yeah, yeah, similar. I have never thought about the different species things in that picture, so that's a very good question.
And what's interesting about the fountain effect as well is not only would you have different altitudes, but that also implies different latitudes and where the gravitational settling. So if there is some mass dependent processes, it would also have a longitudinal effect that could be interesting if you had more heavies closer to the equator. Great. Any other questions for Shasha? Yeah, so the next LWS, we've had solar dynamics observatory images shown. We haven't had a lot of Van Allen probe, but we have had some discussion on Parker solar probe, but the next one's going to be GDC. So that's really going to be looking at this ionosphere, thermosphere, and how energy from below and above drive the dynamics and the structure of the ionosphere and thermosphere.
Yeah, yeah, exactly. Yeah, we haven't had such a mission, that is able to measure both the neutral and then plasma species in the polar region for a long time. The last one was like the DE2, right? Yeah, the simultaneous measurement. Yeah, so really looking forward to that. And I do hope that, for the magnetometers and also the drift meters that are in the competitive phase A, they will select, those two instruments. I think that's what people expect, right? They will select at least one instrument for each type.
I'm on one of the drift meter teams, so I hope they select us.
And I'm the PI on one of the magnetometer teams, so I hope they select us.
They should take us too, and then just not worry about the rest of it.
Yeah, that's how it. Great. And
what are your power and weight and bandwidth constraints on the magnetometers, Mark?
So yeah, one of the big issues is not so much power and weight per se. It's they're expecting a short boom, which will make it a very noisy environment. And then manufacturing, there's going to be at least 6 spacecraft, and so you need to make 6 to 12 magnetometers, which is difficult to do in a typical mission phase. So GDC is a little bit unique because it's going to be the largest constellation that NASA has had.
So being able to make the same thing over and over, you have to come up with a jigs and
That's right. Yeah. But when you look at Starlink, they're hoping to launch 30,000 satellites. So people are starting to think about designing for manufacturing and how to test and manufacturing. We're not yet at those thousands of spacecraft where you can have a loss of 49 Starlink satellites in one loss, and that's not a huge impact. I mean, it's hundreds of millions of dollars, but in terms of the constellation. But Miguel, a question.
For you, Mark, no one has thought of contacting Starlink or anyone else for putting instrumentation on them?
Yeah, so there are different classes of missions, and the class depends on the reliability. And since this is one of the major LWS missions, it's a Class C mission that has high reliability and low tolerance for risk. So Starlink has taken the opposite effect. We need to build a lot of them, and if a certain fraction of them fail, that's okay, where NASA doesn't want any failures. So, but we're learning trying to learn from each other on how to do things. But and that's one of the problems with failure is not an option. The mantra of NASA is if you are afraid to fail, you will never innovate. You'll never try anything new. And so trying to get that balance between low risk and innovation is always the challenge. And so for students too, as you go into your dissertation proposal, obviously you are going to make discoveries, but how much risk are you willing to take? What if it fails? Did you still move sort of the frontier of knowledge forward? So thinking about that balance is key. So Nick, where should we go from here?
Well, I think we can continue the office hour / discussion phase, but also it's meal break, so people should get a meal and be back by 12:30. Be back by 1/2 past.
So about 25 minutes from now.
25 minutes from now, yeah.
And feel free if you have any last questions for Shasha to stay on.
That was my way of making sure my microphone worked.
So I can get we can get a check on whether who's here, and so either turn your cameras on or give a thumbs up, and then I'll turn it over to Christina.
Great. Looks like we've got most people we're expecting. Excuse me. Seem to be losing my voice. Too much talking. All right. So we're moving on to our next lecture for the day. Matt, you want to just? I actually haven't met Matt. So hi, Matt. You want to go ahead and introduce yourself? You're muted right now.
There we go. I figured it out.
There you go.
Can everybody hear me all right?
Yeah.
Yeah, so yeah, and I apologize for not participating earlier. I had a bit of a whirlwind last couple of weeks, but I'm glad to be here today. I'm Matt Zettergren. I'm faculty at Embry-Riddle Aeronautical University. I have been there for, I guess, almost 15 years now. And my area of expertise is ionospheric physics and space plasma physics, and my sort of main research approach, I guess you would say, is numerical simulation. The students who work in my group and the papers that come out of my group are mainly simulation papers. I guess that's about it for starters.
Sounds great. I will, as I'm sure you saw happen before, if there are questions, you don't have to monitor the chat. If there are questions in there that I feel like, it would be great to interrupt you, I will try and get a word in edgewise and interrupt you and have the questions, or if somebody raises their hands, I'll try and keep an eye on that.
Okay, awesome. Yeah, and to everyone attending, please, interrupt me, ask questions. I have quite a lot of material, but I'm perfectly happy to just talk about whatever aspects of this that you all find interesting. Let's see.
So why don't you get started?
Share.
Yep.
I'm inevitably going to do this on the wrong screen. Is this? Let's see.
That looks good.
Okay, good. And then I should be able to bring chat on my other screen so I can see it. Wow, fancy. All right. Okay. Yeah, so I'm gonna talk about modeling the terrestrial ionosphere. Almost everything I'm going to talk about can be applied to a planetary ionosphere. Some of the conditions would necessarily be different: plasma beta, level of collisionality, so on and so forth. But the basic ideas are going to be very, very similar. I focus on the terrestrial case for two reasons. One, because Shasha just talked about it, and two, because I understand it better than other places. But a plasma is a plasma, right? And if you have some approaches to describing it in one regime, you may be able to convince yourself that you can study it in another regime as well. But you would also better be a little bit careful. And we're going to talk about actually a range of modeling topics. The first part of this I focused around just talking about why we would want to do modeling and what basic types of models there are. And then I'm going to give basically a slate of example model applications. And a word of warning, these are very heavily biased towards my own work because that's what I'm most familiar with and have an easiest time answering questions about. But really, the different ways in which we use models, you could take anyone who has done model development and you'll find that they've applied models in all of these different ways to do theory, to assist with data analysis, to do mission planning. These are sort of common things that we do with our numerical codes. The second part of the talk, which I'll get to after the break, is going to be more technical and more focused towards how one would go about designing a model. And there's no way you can cram all of that into one 45-minute discussion, but I'm going to sort of sketch things out and give you some example codes and do some demonstrations and with the thought that probably someday later in your career you'll read an entire book on the subject of numerical modeling, or you'll take a computational physics class at some point, whatever the case may be. So this is going to be less organized than Shasha's presentation because because I'm not Shasha, and also because there's no textbook that you can go to and look up ionospheric modeling. Really, a lot of this comes from just dozens of articles and textbooks that I've read over the years. Some of them have nothing to do with ionospheric physics. It's about numerical stuff. So it's really, it's going to be a bit of a far-ranging discussion. And like I said, please, whatever you find interesting, feel free to ask me about. I'll provide the slides anyway. You can always go back and read those later if we don't get to all this. Let's see, my mouse doesn't work. Oh, here we go. So I'll start by, rearranging ghost windows here, talking about why we need modeling tools. And some of this is fairly obvious, but I think it's kind of funny. I sat down to write this, and it actually required me to think a little bit about how I would classify like my different research activities involving the simulations that we do. And so one way, and this is very relevant to what Shasha talked about, one of the things she emphasized over and over again in her talk was that the ionosphere and thermosphere in which it's embedded are extremely tightly coupled together. And to a large degree, the question of what the ionosphere is doing is very dependent on what the thermosphere is doing. And so that's an example of sort of conceptually discussing the connections between different systems in the space environment. And I think that's actually one of the great uses of models. And I'll show you some examples of thermosphere ionosphere coupling studies and the kinds of things that we look at and how we understand the impacts of one of the systems on the other. But another example of that would be Michigan's space weather modeling framework as well, where you have ring current models coupled to magnetospheric models, coupled to ionospheric models, and so on and so forth. The purpose of doing that is, well, one of the purposes is to understand how one of the systems affects the other. How does the ring current affect shielding of electric fields from lower latitudes in the ionosphere, and so on and so forth? Those are the types of sort of questions we ask. So by way of a warning, the beginning of this is going to be a little bit of a philosophical discussion, but I'm going to really very soon dive into a lot of different examples. So prediction is always something that's on our mind. Shasha talked about radio environments and what implications the ionosphere has for that. The website here is NOAA's SWPC website, which I highly recommend. I bet you've already been there and someone has already showed you this, but you can get an idea of what's going on the surface of the sun from the different in the solar atmosphere. The Earth's particle environment is what I sort of drew a box around here, because this is actually a model of sorts that produces an estimate of where the aurora is going to be, what the planetary activity is, and we talked about GOES a little bit earlier too. This is a nice resource, and I'm going to try to give you some other resources if you're interested in either using models or contributing to them or developing them for your own purposes. But prediction is important for a number of reasons, and I've circled, it's actually very tiny print, but you can see them up here. Radio communication we talked about. Aviation, positioning, and navigation is affected greatly by the state of the ionosphere, how accurate your GPS is. Applications of this are increasingly prevalent. Aviation is one of them. You have precision farming and various other applications that could be affected by this. Of course, everyone talks about the power grids and geomagnetic storms. You can have ground-induced currents. These are very sensitive to the state, the conductivity of the ionosphere and the state of the convection of plasma. Satellites, anytime you make the thermosphere expand by dissipating Joule energy, for example, you're going to cause increased drag. And you probably, I believe it was the Starlink constellation a few months back that actually they had launched some satellites into very low Earth orbit that were immediately deorbited basically because there was a geomagnetic storm with enhanced drag. So probably that's been mentioned. That's sort of one of the most spectacular sort of failures to anticipate space weather. And then there's various other things that we've mentioned here. So being able to predict what the ionosphere is doing is something that you can do with models, and it has practical implications. This third item here is something that I do quite a lot, which is sort of hypothetical or theoretical investigations. Here, you're not really trying to predict the state of the ionosphere for a specific event, or model the state for a specific event. You're more trying to understand how different bits of physics actually impact your system. So in our case here, for this discussion, the system is the ionosphere. And you might ask questions like, how is Joule dissipation affecting the thermosphere? How do different terms in the continuity affect the transport of, in the continuity equation, affect the transport of plasma? How do polarization effects manifest into plasma density irregularities or something like that? These are all questions we talk about, and they're really theoretical questions. It's a physical process and then how it manifests in a complicated nonlinear environment. That's really something you need a model to answer. And then lastly, is probably one of the most common activities that I do is no matter how many spacecraft, how many GDC spacecraft we put up there, we're not going to have perfect coverage of the entire space environment. And sure, yes, we can resolve certain wavelengths and so on and so forth. But the fact of the matter is there's going to be a place for modeling activities in the interpretation of data. We don't always have the data coverage we need. We don't always have the context, the larger scale context of what we need. And models are particularly good for sort of filling in some of those details. You can do a global simulation and then sort of understand, okay, here is the environment through which my single satellite flew. And so therefore I have sort of some idea of what the conditions were and some idea of how anomalous my measurements were, using the word anomalous, compared to, you know, expectations from a model, or probably said more properly, how anomalously poor the model results are compared to reality. Anyway, there are always two sides to this. And yeah, on that topic, I will caution you that ionospheric modeling, sort of the state of the field right now, and I probably should have made a slide on this, but by no means can we really do high quality prediction of the ionospheric state. This is true of even the day-to-day variability of the ionosphere. There are probably wave and tidal effects that we aren't incorporating. And so if you just run an ionospheric model for several days, chances are what you're going to see deviates substantially from reality. And that's just the state of the art right now. Similarly, when we're simulating sort of not global behavior, but smaller scale parts of the ionospheric plasma, we often find enormous deviations from data, and it's mostly sort of unaccounted for physics, or at least this is my impression. And at the very end of this whole unit, I'll say a little bit about sort of where I think we are, which I've sort of just summarized, and then where I think we need to go to try to start addressing some of the relatively big problems that we have. Let's see, sorry, I keep losing my mouse. So just a few comments on basic modeling types. I've kind of at the highest level, I've separated these into empirical models and physics-based models. And by way of a warning, I'm going to spend most of the time talking about physics-based models because that's my area of expertise. But empirical models play a very, very important role in space systems modeling. I've shown, for purposes of the ionosphere, what is probably the most common empirical model in the ionosphere at the top right here. This is the IRI model. And Shasha talked about the meaning of NMF2 and HMF2. Those are the left plots. And then the right plot is total electron content, but without the factor of 10 to the 16th divided out for some reason. So anyway, this is basically a measure of the column density of the ionospheric plasma, column density in the vertical direction here. It gives you an idea of the total amount of plasma. You can sort of see an equatorial ionization anomaly, but there's some other stuff going on here that makes it kind of complicated. So IRI is probably the most common model. It's particularly used a lot at mid and low latitudes. The way this works is these are based on very large data sets that are basically accumulated, binned, and more or less fit to some sort of basis functions in order to produce a predictive model for, on large scales, what roughly the ionosphere looks like. Now, the other side of the coin here is what I'll call a physics-based model, which is it has in it, it's not a statistical treatment of a bunch of data, as is an empirical model. I mean, that's a very reductionist view of what an empirical model is. But anyway, we'll go with that for now. But a physics-based model it has some either physical principle or set of mathematical equations that sort of underpin the code. These equations are being, or physical principles are being simulated in the code, and it produces an output. And I've chosen to use GITM as my example here. This is total electron content, so the same thing that was being plotted from IRI here, but a lot of GITM's focus is high latitude dynamics. And so this is showing sort of a polar view of the globe here. So these are sort of the two types of models I would distinguish between. This is mostly sort of for your information. I think this might be like a more useful slide when you guys are going back and when you all are going back and looking at, some of these things. But it turns out, and I actually was not aware of this till I was sort of poking around while I was putting this together yesterday, but CCMC at NASA has really nice interfaces for a lot of the empirical models that people commonly use. Now, you won't always want to use a web interface to do your simulations. A lot of times you'll want to download source code because it's going to be a lot faster. But if you want a quick idea of what the IRI ionosphere looks like, or if you want a quick idea of what the MSIS thermosphere looks like, these are wonderful, wonderful. And I put all of the links to the different models here. These are wonderful resources. I've also put sort of a very simple description of how an empirical model works here. Really, the models are only as good as the data that underpin them, number one, and number two, the specific choice of basis functions. You can really mess yourself up if you choose a bad basis to work in, and there are all manner of examples of this. There's some situations where spherical harmonics are a great choice. IGRF is a good example for that. There's some other situations where they can produce problems sometimes. I'm not saying that Ampere should be doing anything different, but you definitely get drumhead artifacts from using spherical harmonics for those fits. I'm not sure what the alternative would be, but I'm just saying you need to be aware to a degree when you use these models, what some of the limitations might be, and to an extent, how they're built and how they might manifest numerical artifacts. All right, so we talked about international reference ionosphere, the mass spectrometer. This is the bizarrest name. It's mass spectrometer and incoherent scatter. It's an atmosphere model. It's the most widely used atmosphere model. It gives you densities and temperatures of the neutral atmosphere, basically from the ground to exabase, and it's based on mass spectrometer and incoherent scatter data. as you might imagine. It's really a climatological model. And that's true of all of these. These are based on averaging and binning really large sets of data. You're not going to see a huge amount of day-to-day variability in these models, and you're definitely not going to see like geomagnetic storm-related features like LSTIDs or strong joule heating or stuff like that. These are going to probably average over all of these. Nevertheless, they're incredibly useful for certain applications. MSIS does not give you the atmospheric winds, which are actually really important to understanding ionospheric dynamics. And Shasha gave one really good example, which is the ionization anomaly. It's ultimately generated by a neutral dynamo. And so the HWM model is kind of our state of the art for that. And then at high latitude, Shasha didn't get into this too much, but there's two super important energy sources at high latitudes that are actually quite difficult to account for in models in an accurate way. So that would be the plasma convection that's imposed by the magnetosphere and solar wind, and then of course the energetic particle precipitation. So Weimar convection model is one way of computing a convection pattern for the ionosphere, and then Ovation Prime will give you a really sort of averaged out idea of what the roll zone precipitation looks like. Let's see, Nick Gross says, talk to model developers if you're going to do published science with their models. This is good advice, and it's not necessarily because of attribution. It's more if you want to make sure the things that you're looking at in the model are not numerical artifacts. The best person to ask is one of the developers, like, hey, we see this feature in the model. Is there a way to test whether this is real or not, or whether we're looking at some sort of inner failing of the numerical routines, which I can show you some examples of those later on. Yeah, and it is also good advice for using public data too. I always try to put someone on my studies who knows sort of the inner workings of the data processing that I'm using, because I'm not a data person, and I'm always worried that I'm going to make an incorrect conclusion based on sort of a misunderstanding of how the model was run or how the data were run. So those are widely used empirical models. I put that slide mostly as a resource. Physics-based models, so there really are more than I could possibly list here. What I did is I got a little bit lazy and listed the ones that were most familiar to me, but please be aware that there's an enormous number of what I would call bespoke codes, which are developed by very small groups, and they're aimed at very specific problems, and they're often very efficient and effective at solving those problems. In contrast with that, there are also a number of sort of general purpose codes that kind of aren't really geared towards a specific problem, but are more intended to be a general tool for, example, interpreting data, or, working with mission design or something like that. And then the other thing that I would highly emphasize, and, these talks are going to be these discussions are going to be very biased towards my own work, because of course that's what I know best. But please understand, there is no necessarily best model that can address all aspects of ionospheric science. And I'll go back and touch on that in a lot of detail in the second part. There's certain physical paradigms that you need to observe when you're looking at certain scale sizes and so on and so forth, and you need to choose a model which can resolve those, both in terms of the physics that it includes and then the actual discretization and resolution of the model. So I'll talk about some of those issues in more detail later on. There are several very widely used global ionosphere thermosphere models. GITM, which is my colleague Aaron Ridley's model. It's been used by a large number of groups. It's the sort of special thing about GITM is it's non-hydrostatic, so you can investigate a number of atmospheric wave phenomena and couple those into the ionosphere. So a lot of the recent work that's been done with GITM is very focused on understanding wave activities. It's a good tool to do that. TIGCM is a global circulation model, hydrostatic. It's incredibly efficient. It runs much faster, for example, than GITM or my own model, Gemini. So it's a really good tool for running out predictions for long periods of time. based on some initial conditions, what do we think the thermosphere is going to look like at some later time? And WAM-IPE is kind of in the same vein. It's used by NOAA, developed by NOAA, and it's really, I would kind of describe it as sort of an operational atmosphere ionosphere model. Those are all global models. You also have local codes, which are intended to be run at really high resolution, but they don't have the global context and global coverage. And I listed my own code, Gemini, there, which is, can actually look at it. I believe, yeah, so Aaron's got his code on GitHub. I've got my code on GitHub. If you want to know what's involved in making these models, you can actually go flip through the source code. It's a lot of work. I would say I've probably, so my code actually started out as kind of a bespoke model. I had a very specific problem that I was solving. I wrote a code to do that. I solved, at least to my own satisfaction, that problem. And then I basically set it aside for a while. Okay, I'm on to the next thing. But then people kept asking me questions. Can you do this? Can you do that? And it kind of grew into something more general. So I think that's not an uncommon thing to happen, but it's a process that really encapsulates several years of active software development. So fortunately, depending on what you're trying to do, you don't need to always develop your own code. And in fact, for certain things, I would really not recommend that. So this is, you start with a mathematical model of the system, you discretize your equations, you have your numerical solutions, and you have to be extraordinarily careful about selecting algorithms for this. I will return to that issue later on. There are some really important caveats to observe. And then I put down visualization of results here. Your results pop out of the model as a bunch of 3- and 4-dimensional arrays of numbers. And for example, the bats or us simulation that Shasha showed, the magnetospheric dynamics. I cannot even imagine how much work is behind trying to visualize that. You got to draw magnetic field lines, you got to take slice planes through, you have to put together a movie. It's really a lot of work, and it can, especially from an educational perspective, it's important to have good visualization so you can quickly and effectively explain what you're doing to other folks. So I think the remainder of my first part here is really talking about different scientific applications of models. I wanted to start with sort of showing you what these things do and the kind of outputs that we look at and the types of problems that we try to solve. And as I walk through this, please, feel free to ask me questions about the specific examples or studies. A lot of these are in various repositories online. You could actually rerun some of these if you wanted to. And all of the examples I'm going to show are just from my particular ionospheric model, Gemini. But again, if you talk to anyone who's done model development, they'll have examples of, using modeling for theory or using it to interpret data or for mission design, which is actually, I didn't say too much about that, but that's something I'll sort of mention at the end. And again, please, I use my own examples because they're easiest for me to explain and quickest for me to put together slides for too as well. All right, so this is really almost a sort of survey / slideshow / just lists of different uses of models. And I wanted to first talk about what's probably one of my favorite modes of using a model is really taking a physics-based model and trying to dig specific bits of interactions and physics out of it. How does process A affect the overall evolution of the plasma in the ionosphere? I think it's an incredibly useful way to use a model. And there are certain questions that only models can answer. And I guess one good example of this that I'll talk about in a minute is for studying plasma turbulence. And one particular aspect of this, I'm not sure anyone has talked about this, but there are these features in the polar cap ionosphere called polar cap patches, and they're often associated with turbulence in the plasma and instability. And a particular part of our field is studying, including some of the research Shasha does, is studying how these patches form, why they become unstable, what are the energetics surrounding the dynamics of these patches, and so on and so forth. So, study of plasma turbulence is kind of one good example of a use of a model. And one reason a model is a good tool to study that is because, aside from doing observations, which are going to necessarily be incomplete, your other way of studying this is really linear or quasi-linear theory. And the issue with linear theory of an instability is you really presume small fluctuations, and all of the results you get, the growth rates, the wave numbers, the character of the instability as it grows, they're all dependent on there being small perturbations. And that's simply not going to be the case for that long if you have an instability or a turbulent situation that's developing. So it's a good use for these types of models. So I'll also use this as an excuse to talk a little bit about ionospheric dynamics. This is a high latitude phenomena, like I mentioned, since Shasha kind of stopped short of that. But the way this works, and I don't know if you can see my cursor or not, but at the bottom you have this blue region. It's a large plasma density. The white region is representing a low plasma density. You have a background magnetic field and a background electric field. This is presumed to be part of some larger global convection pattern. The plasma is moving, therefore there's an electric field. And because of the inhomogeneity in the plasma, what you end up with is preferentially larger currents in this dark blue region, which terminate and produce charge densities. Now, the charge densities themselves, electric field goes from positive to negative, produce response electric fields. These are in addition to the background electric field. And these response electric fields from this initial sort of corrugation here generate their own E cross B drifts. Oops, I am sorry, I went backwards. So there's the response electric fields, and here are the E cross B drifts from those. So what you'll notice about the E cross B drift is this initial wave-like pattern, this initial corrugation is going to be further emphasized by the fact that you have these charges accumulating on the edge of this patch-like structure. So that's the bit of plasma physics behind the destabilization of polar cap patches, at least as we understand it in the simplest possible form. And like I was saying earlier, it's a nice candidate for modeling because this situation very quickly evolves into something that you would really qualify as turbulence in the sense of sort of a steady state cascade of structures of different scale sizes. One of the science questions, and you will see, particularly in the second part, you will see a fair number of equations. You can't do physics-based modeling without equations. It's just not possible. And I'm happy, either after the fact or while we're doing this to explain some things better. But one of the questions that was asked about this specific case for instability in patches is, what physics needs to be included in the models? What particular currents vis-a-vis these things that are producing charge density here need to be accounted for when we go to do the simulation? And there's sort of different ways you can think about approaching that. You can do some sort of dimensional analysis. We do this all of the time in electromagnetic theory. For people who do radio propagation, you'll recognize sigma over epsilon naught omega as being ratio of displacement to conduction current. It describes the behavior of radio waves in conducting media. For our case, there's various currents like conduction current, polarization current, which is based on ion inertia, and then diamagnetic current, which is based on pressure. So that's a lot of plasma physics, and I don't really expect you to worry about it too much. But the point here is there are many candidate processes that could actually affect the progression of turbulence in the plasma, and it is something that's really well suited to study with a model. So this is done with our Gemini code, but I've kind of reduced the equations a little bit. There's a conservation of mass equation. There's a conservation of charge equation. We assume to leading order the drift is E cross B, and we assume electrostatic that's this last line here. The only thing that's different between these 4 simulations is which currents I include, whether I'm including inertia, whether I'm including pressure, and so on and so forth. And I accidentally clicked the button, so you'll see the progression run. But this is sort of the definition of a non-linearly evolving system. You have plasma density variations that are up to a factor of 4 or 5. There's no linear or quasi-linear theory that's going to adequately describe this process. And you can see by including different physics, you actually get quite different results. The most striking difference is really the left to the right when you include this polarization current term. And that was really kind of what we were after with this study from a theoretical point of view. You know, what does this process do in the model when you simulate the plasma with it? Yeah, Mark made a good comment. In fluid mechanics, there are all these dimensionless numbers that we use, magnetic Reynolds number, plasma beta, actually, yeah. Anyway, Knudsen number, Lundquist number, so on and so forth. They can often describe what type of dynamics are very important. And actually, there's probably one that I just did a straight ratio of currents here, but this is probably equivalent to some dimensionless number in the NRL plasma formulary. So yes, it's a very good point. There are quick ways of checking what physics you might need for a simulation. I have some caveats on that too. When I sat down to think about this yesterday, I actually came up with some other things. I'll show you another example of sort of modeling in service of theory. And this is a Rayleigh-Taylor instability. You've probably seen these kids' toys. Oh, my kids have one. I should have brought it. Anyway, it's oil and water. You turn the thing over and you see the turbulence develop as the heavy fluid propagates through the light fluid into these, finger-like structures. So everyone's seen that. That actually happens in the equatorial ionosphere as well. We call them plasma bubbles. And the specific instability is called a Rayleigh-Taylor instability. It's really a gravitationally driven process. So in fact, the diagram might as well be exactly the same as for this gradient drift instability that happens in patches. The only difference is instead of a background electric field, the primary current that causes the instability is actually driven by gravity, which is kind of crazy. When you think about plasmas, really the last force you think that's going to really matter a lot would be gravity. But the fact of the matter is, we do need to consider gravity. It's responsible for the law of atmospheres that Shasha showed us in the last presentation. And it plays an important role here. It actually drives a relatively small current, but it's enough to produce a charge buildup and unstably growing waves and eventually turbulence. The specific theoretical study that we were looking at for this was really applications of sources for initial perturbations. Yes, we know that you can generate an equatorial instability in the bottom side ionosphere. And we also know there are all manner of waves present all of the time in the atmosphere. These could be from weather-related sources. They could be from airflow over mountains. These can generate quasi-stationary waves. They could be from impulsive events like volcanoes or earthquakes. I'll show some examples of that later. But the atmosphere is basically royal. It's like the surface of the ocean. You look at it, there are always waves there. They may not be that big sometimes, but they're there. So anyway, the process that we're looking at is, can the neutral atmosphere effectively seed the growth of bubbles? And it's a good application for a model. The first thing we did was basically put in the middle of the domain here. So this is magnetic longitude, horizontal, altitude, vertical. But in the middle of the domain, we put basically a discontinuity in the thermosphere. And we wanted to look at, how effective a relatively small discontinuity was at launching nonlinear responses in terms of plasma bubbles. And the answer turns out to be extremely effective. Even a relatively small variation in the atmosphere over the center of the model domain results in the very fast growth of these bubble structures. Of course, that's not representative of a wave. That's just a simple hypothesis testing. Can a small variation in the thermosphere affect this process? To actually test it with waves, you need a model of atmospheric waves. And this is this is actually a good example of model coupling, like I was talking about before. The thermosphere, if you want to describe it in terms of compressible waves, you need yet another type of model, a compressible atmosphere model. And so we've used one for this here, and you see sort of a spectrum of waves that are generated as a function of altitude and radial distance. These are from what we believe is sort of a weather-like source. And I'll actually play it here. All the numbers don't really matter. These were just to give some quantitative feel, but you see those are infrasound waves being launched into the atmosphere. They dissipate aggressively near the exobase due to kinematic viscosity. And these are actually called atmospheric gravity waves. They're really a buoyancy wave. You can think of a buoyancy oscillation in sort of a stably stratified medium, sort of like the surface of the ocean bobbing up and down. That also happens in the atmosphere as well. You see all manner of structures and ducting and so on and so forth that go on here. So this is actually a very complicated system, and not a system you would want to describe, with pen and paper analytical theory. This is really a modeling problem. It's too complicated to be easily described, even with like a normal mode summation or something. So we were able to generate plasma bubbles from that, but what we discovered actually was that it wasn't particularly that efficient. And the issue here, it doesn't really matter. The point is, this is a use of models to study a complicated physics process. But there's not good phase speed matching between the growing bubbles and the waves that are generating the perturbations. So they're actually fairly ineffective. They do seed the growth of bubbles, as you can kind of see here, but they're not super effective at that. Let's see, question. What do you suggest to begin studying the modeling of plasma bubbles? Yeah, so that is a huge, so the formation of plasma bubbles has sort of occupied a significant part of our field for probably 60, 70 years. These are, so we know basically what produces this, but you can't at all predict them day to day. I don't know which nights, I know which nights they might appear, but I don't know which nights they will appear. And I don't know what specific lower atmospheric processes are coupling to these bubbles. I think what the last decade and a half of research has shown is that there is an atmospheric component to whether the bubbles are produced on a given night, but we still don't know exactly what that is. Is it sort of a larger scale tidal oscillation that's contributing, or is it some of these small scale gravity wave processes? So studying, there's innumerable papers, and particularly in the last, I'd say 15 years, the models of this process has actually gotten pretty good. So if you look at like Joe Huba's SAMI3 model, there's a whole series of papers going back to probably about 2003, where he's modeled various aspects of the formation of these different plasma bubble features. And some of his new work is actually really interesting because he's coupled in the WACM-X, which I forgot to mention is an important global circulation model, but he's coupled that in, and he has shown that the plasma perturbations are quite significant in response to just ordinary atmospheric activity near the solar terminator. So definitely look at papers by Joe Huba and Jonathan Krall, the models SAMI3. Dave Heisel, the Cornell group, has done a lot of simulation studies on equatorial plasma bubbles, and he's also looked a lot at seeding of the bubbles from atmospheric perturbations. There's a is it Nature Geosciences paper from a couple of years ago where they're looking at the effect of neutral turbulence on plasma perturbations in the upper atmosphere. Those are probably, I'm trying to think, there are more groups that do this. Oh, Tetsu Yokoyama is another name. You should look up his papers. He's done quite a lot of instability modeling of this type. I have actually I never managed to publish this because I did this for AGU, and then I had a bunch of other stuff come up. And story of my life, it's 2 years old now, and one day I'll Yeah, Mark asks a good question. And this is actually true of a lot of sort of ionospheric conditions, it's sort of always unstable. It's just a matter of what the growth time is relative to the background changing in the ionosphere for a lot of these. And yeah, certain instabilities, I think with Rayleigh-Taylor, I think the theory matches up okay with what's observed in terms of how quickly they appear, if you account for the neutral sources. So as long as you have something that's really sort of banging against the bottom of your ionosphere, you're going to produce some aggressive growth of bubbles. If you don't have seeding of the bubbles, you're not going to get them most of the time. I think that was effectively what was concluded a while back. Yeah, there are other instabilities like Perkins instability, which for whatever reason seems like it should never grow, yet we see it all of the time in the air glow. So there's some other bit of physics there that's going on. That's another good example. If you look up, like I said, Tatsuyoki Yama's papers, he has some attempts to theoretically explain why they appear, Perkins instability appears so much faster than what is suggested by just the linear theory. So yeah, and then there's really no great textbook resource. I think Mike Kelly's book does talk about bubbles and probably gives the standard linear derivation, which you should go through if you're interested in that. You know, like I said, my caution with linear theory is what it always is. Just understand that this only applies like at the very beginning before anything interesting happens. I'm being a little bit glib there. So I'll talk a little bit about you know, uses of models to interpret data here. I'll actually look at two examples. So this is another turbulence example. I'm actually going to, you guys can feel free to look through the slides on this. I want to pop over to one that's maybe a little more pertinent to what we just talked about, which is the coupling of the thermosphere to the ionosphere. Something kind of interesting that has really become apparent in the last 15 or 20 years, especially the last 10 years, is whenever you have an impulsive source like an earthquake or some other natural hazard, anything that displaces the surface of the earth, you produce waves in the atmosphere. And for the most part, if you're talking earthquake and volcanoes, these are going to be really long wavelength infrasound waves. If you're talking weather related sources, it's going to be a mixture of like infrasound and atmospheric gravity waves. But anyway, these waves will perturb the overlying ionosphere in actually a fairly predictable way. And what people have started to do is look at studying the near field structure of faults, for example, seismic faults using perturbations in the ionosphere. Now, these are post-seismic perturbations. So please understand there's also a body of literature about pre-seismic, in other words, variations in the ionosphere before the appearance of, before the main shock of an earthquake. My opinion is that those are not super well supported by the data at this point. Just to say that you see a structure in the ionosphere before a seismic event, I find it to be not well supported by the data. I'm not saying it doesn't happen. I'm just saying that the observations that we have do not demonstrate it very conclusively, in my view. Nevertheless, after the seismic event happens, there's no question that there's all manner of tsunami and surface perturbations that generate these waves. So one thing we were looking at and trying to interpret from the standpoint of data, I've actually circled it up here, but after this large earthquake off the coast of Japan, you end up with this really this blue area here. It's kind of a hole in the ionosphere. And I'll pull this back and play it again. You can kind of see, you can actually see the infrasound start to pop up here. The waves sort of progress in this direction, and then you get this really deep hole in the ionosphere. And it sort of slowly fills in with time. We were trying to understand whether that was an artifact of the data filtering or whether that was actually a physical process that could produce a hole in the ionosphere. And one sort of interesting indication, it was when we do the binning of the GPS data from the Japanese GeoNet network, it's very longitude dependent. So it's very sort of sensitive to directionality in the sources. So we really kind of thought that this was probably, we didn't do any spatial filtering here. So the fact that there was some dependence there was sort of suggestive in the data. But this is another thing, these are very large waves, and you can see this is actually an infrasound shock wave in the lower ionosphere right here. The perturbation from this earthquake, which was magnitude 9, was absolutely enormous. And this shock wave is sort of what we were hypothesizing was possibly strong enough to push the plasma either away from the epicenter region so that you left a hole there, or to push it down enough so that it recombined really quickly. That's kind of what we were looking at here. And I'll show you this simulation just so you can kind of see. This is the manifestation of infrasound in the ionosphere. So these are actually plasma drifts, but they're largely forced by infrasound shock waves. So kind of the most obvious thing about this is there's actually an acoustic resonance, and it's between probably the ground and the thermosphere temperature gradient. You actually sort of set up a resonant cavity there, and you get a lot of sort of normal mode ringing, which was pretty surprising to us how long that lasted. But we actually went back to the data, and it's there plain as day, right? You can see all these little oscillations there. Those are not artifacts. Those are actually, that's ringing at some normal mode for the ground thermosphere cavity. So anyway, it turns out we did the analysis for this, and it is largely transport related. The plasma is being shoved, I believe, southward in this case, and it's accumulating away from the epicenter and leaving a hole. And we were actually able to reproduce these data fairly well, so we feel like we have some idea of what's being done here. The other thing that we were doing with this event that we were trying to model was we were trying to figure out, people have observed magnetic perturbations after earthquakes as well, and we were trying to figure out if the ionosphere might play any role whatsoever in that. In other words, you have these large shock waves that are passing through a region that's fairly highly conducting. It's not completely insane to think that you might have a dynamo current in a magnetic perturbation, and indeed you do, but it's incredibly small and incredibly difficult to measure. And on top of that, you also have moving seawater because of the tsunami for this event, and that's another candidate source for motional EMFs and currents. So that is still, as far as I'm concerned, an open question. What are these magnetic signatures that we often see?
So Matt, we're approaching the break time. So wherever you get to a good stopping point where we can take a 10-minute break.
Yeah, sure. Let me go maybe one or two more slides. Would that be okay?
That's fine. Yeah,
Okay.
whatever, whenever is a convenient spot. Yeah.
Yeah. Okay, so the last sort of application that I wanted to talk about was modeling for mission design. Back to the topic of polar cap patches, we're actually actively developing a mission to try to study these, and I wanted to just emphasize that a lot of the simulation work that I do nowadays is really in service of mission design. How do we know that we have an orbit that will allow us to answer our science questions? How do we know that we're making the correct measurements at the correct cadence that allows us to answer our science questions? One thing that's great about numerical simulations is that, yes, you get an output that's a complete picture of the system. You can fly spacecraft through this, virtual spacecraft. You can fly through the model. You can actually generate synthetic data and synthetic measurements. And so that's exactly what we do. This is a patch-based mission. So we've taken some of our simulations of patches here and simulated what it would look like if you had an overflight with two orbits at different altitudes here as the patch starts to destabilize and structure, or whether you have an orbit that's a revisit at a 1-minute cadence. So this is just sort of an example of investigating pros and cons of different types of orbits for a 2 spacecraft configuration. So the key idea here is that, and I think this is sort of where I'm going with a lot of my research, is trying to help design missions that are, you know, can demonstrably close their science. We can demonstrate with synthetic measurements that I can apply my processing techniques that we propose at the measurement cadence we propose, and actually distinguish between different types of plasma instabilities in the patch, for example. This is another multi-spacecraft mission, actually 2 of them that we're doing modeling work for as well. So this actually occupies a lot of my time right now. I'm also on one of the GDC teams, as I mentioned. So I think I'll, like I said, after the fact, you guys can feel free to email me questions or ask questions now, but I think that was actually, yep, that was the end of the first part here. Does anyone want to ask any questions about modeling? What is it like to be a modeler? I don't know, anything like that?
Yeah, people feel free to unmute and ask a question or raise your hand.
You got into modeling because of the money and the fame?
Yeah, exactly. No, it's weird. I kind of backed into it. It's I worked with Josh Simiter at BU for my undergrad, and he's actually an optics guy. But it turns out, like, in that group, what was needed more than anything else was some ability to interpret some of the measurements that we were making. And so I just sort of, I had a background in, my undergraduate degree is in software engineering. So I had a background in software engineering. So it was like sort of, everybody sort of looked at me and was like, well, you're the software engineer. Can you figure out how to do this? You know, how to do simulations to help with this.
All right, Nick, do we want to take a 10-minute break? Maybe.
Sure.
Okay, so we'll take a 10-minute break, and if people have questions, I mean, I'm sure Matt's going to be here. You can check the chat, you know.
Yeah, feel free to put stuff in and I'll answer it to the best of my ability.
Okay. So we'll just start up again in 10 minutes.
Strong opinions. Okay, so this part is going to get a little more into the nitty gritty, and I'm going to try to float over the top of a lot of details here and sort of, excuse me, give all of the materials to you all later and some example codes of how you go about solving numerical problems, how you go about solving modeling problems. And really, I guess the thing that I want to emphasize just up front here is that really modeling is a very hands-on thing. How did I learn to do this? I learned to do it by working out equations, pen and paper, like what I needed, actively coding, trying different techniques, learning different techniques. I had a couple of computational physics courses when I was in graduate school that were incredibly helpful. I had a software design background. And you know, it really is, like I was saying, it's a hands-on thing. You got to get in, you got to dive into Python or whatever, start trying some little numerical codes and playing around with them. There's a lot of tinkering involved in learning how to do models. At the same time, if you don't have to develop a model yourself from the ground up, you should really think carefully about whether you want to do that. Like some folks will want to do that. They actually want to understand the guts, the insides of the models. And I think that's great. That's how I am. That's how I learned, like digging through other source codes. That's how I learned a lot of, you know, the tricks of the trade, so to speak. They're not tricks, they're really techniques. But at the same time, if you know there is a code out there that does something that is useful for your data interpretations, why not use it? Like you may spend years developing your own model from the ground up, and that may be great. It may actually be better than a lot of the stuff we have to offer, you know, currently, but it's also going to potentially suck up your entire life for several years. So you should think about, you know, what you're trying to do, what you want your career path to be. Do you see yourself as a user of codes, in which way, in which case you need to learn how to use them, manipulate inputs and outputs. You need to learn a little bit about how the internal workings operate so that you don't, draw bad conclusions based on essentially errors in the simulation. Or do you need to do development? Is there some thing that models cannot do that needs to be done for your science? And so I would suggest, and for me, I work on these codes at night sometimes. Like it's almost a hobby. Like I'm a computing enthusiast to begin with, and so to me it's not just a tool. It's also just something I enjoy doing. All right, so let's talk some basic physics, numerical implementations, and future needs here. Sorry, I'm kind of rambling there. So Shasha talked in great detail and gave an amazing lecture. I always love hearing people talk about stuff that I sort of already know about or think that I already know about, because I always learn something that I didn't know before, but probably should have known. And so that's how I feel about Shasha's talk. It was really nice. But one of the Boris correction, I'm going to have to look at that, Mark. Is this the div B correction?
No, Slava Merkin lectured yesterday and gave some under the hood things.
Oh, okay.
One thing he didn't mention was that MHD models reduce the speed of light.
Oh,
just so
yeah.
you can do things, but
the speed of light is honestly really inconvenient. I'll explain why later. Actually, I'll show you a simulation that does resolve the speed of light, and you'll see how far we get into it. All right, so the ionosphere is a plasma ionized gas. Shasha talked at great length about how it's produced. But from a pure physics point of view, I'm going to take a step way back. We're not even going to talk about ionospheric physics for a fair amount of this discussion. A lot of this is going to be like a basic plasma physics and basic electromagnetic theory. But what you know from plasma physics is that you need, or if you haven't taken it yet, what you're going to learn is you really need two things. You need a description of the motions of the charges, and that could be in the form of momentum or energy equations or conservation of mass. And you need some descriptions of electromagnetic fields. Now, there are many such descriptions that you could use, and we'll list some of them out, but the decision that you make about how you describe particle motions, for example, has a massive, massive effect on how efficient your code or your model is going to be. So if you don't need to resolve kinetic processes, for example, and I'll explain what that means in a minute, please don't, because you're going to waste a ton of computing time. So this is an important decision, like which code, what type of code do you grab out of the possibility, or what type do you set out to design? You need to very carefully examine what it is that you're trying to do, what physical paradigm you're operating in, and how much computing power you have access to, frankly. So this is fairly reductionist, but I think it kind of covers the major aspects of how we describe plasmas. So I've got 4 different blue boxes here describing 4 different mathematical models effectively for how you would go about describing a plasma. I've sort of drawn a line down the center and divided these into, kinetic descriptions versus fluid descriptions. And this is largely a distinction of microscopic versus macroscopic point of views. And if you've taken a course in statistical mechanics, you're sick of hearing these words probably. But the idea is when you talk about, for example, a glass of water or something like that, there's different ways of discussing it, right? You could discuss it at the level of a bunch of H2O molecules that are together, and there are intermolecular forces that are acting between them. This gives rise to viscosity and various other macroscopic properties. Or you could talk about it in simpler terms. It has an average mass density. It has an average temperature, which may vary from position to position. And it has an average flow speed on, it's not to say every molecule is moving a meter per second or whatever. It's simply that the average bulk motion is in that direction. And that's really largely the distinction between kinetic, which is kind of a microscopic description, versus a fluid description. They're sort of different flavors of kinetic descriptions. If you've ever heard of the Klementovich equation, it actually describes the kinematics of all of the particles in the system exactly. And it's pretty obvious why that would be impractical or infeasible. The peak of the ionosphere is 10 to the 12th particles per cubic meter. And then the ionosphere is several, hundreds of kilometers tall. You can sort of do the math there. There's absolutely no way you can resolve all of those. There are some tricks that you can play, but exact descriptions are fairly uncommon. I'll show some examples of them in a minute. They're not actually exact. They're sort of quasi-exact, but anyway. You could take more of a probabilistic point of view rather than describing the kinematics of every single particle in your system. You could say, well, on average, I have X number of particles between 1 EV in energy and 2 EV in energy. And so in that case, you're sort of discussing the matter in your system in a probabilistic manner. Like if you pick a particle out of your system, it's this probability that it is between these two energies. And that's what we call distributions of particles. And this relates to the Boltzmann equation, which describes effectively the evolution of the probability density, if you will, of particles. And here I've shown an example of a Maxwell-Boltzmann distribution. This is what it looks like in thermal equilibrium when you have frequent collisions. If you've taken stat mech, you've seen this 8 billion times, Boltzmann factor, e to the minus e over kt, right? But anyway, this is potentially a very complicated distribution. It could be out of thermal equilibrium, for example, but nevertheless, you could still discuss it as if it were sort of a probability density rather than a description of every single, lattice site in your solid object that you have. So you can average over distributions. Like you could take this thing here, this is a Gaussian. You could exactly describe this with 2 parameters, the width of the distribution, standard deviation, and then the mean. If you have a distribution that can be described by very few parameters, this will be amenable to what we call a fluid treatment, which is effectively where you average through the probability density and you only track the evolution of these macroscopic parameters like pressure, temperature, and density. And then you can go even a step further beyond that, which it sounds like you all had a talk about MHD simulation, where you're actually, instead of tracking individual types of particles, you're actually just tracking one overall fluid. Which in terms of the magnetosphere is kind of a good idea because first of all, you have just protons and electrons, and you can kind of track the electrons through the generalized Ohm's law. I believe you guys probably talked about that a little bit. So there's sort of a shortcut single fluid model that is applicable in some situations. So I will say one thing sort of categorically up front. Pure MHD does not work well in the ionosphere. The reason it doesn't work well is because it is actually the thing that Shasha discussed in great detail. There's an enormous amount of chemistry in the ionosphere. And what this requires you to do is it requires you to track different types of particles as separate fluids at a minimum, as separate particle types. Why? Because the chemical reaction rates depend on the density of the reactants. So you have to know all of the reactant densities or you can't get the chemistry right. If you don't get the chemistry right in the ionosphere, you're missing 80% of the problem, basically. The ionosphere is a reactive flow. You can't have it without the chemical reactions. So MHD, now, I will say there are clever ways of tweaking MHD so that you can do multi-species transport with it, but it's not commonly done. If you really want to see examples of this, I can give you some recent papers. So anyway, those are our physical paradigms. I wanted to present some examples of techniques or modeling methods that use what I would call sort of a quasi-exact description. As Mark and I were talking about earlier, I'm a BU graduate. And so when I took plasma physics, I took it from Mears Oppenheim, who is sort of in our field of ionospheric plasma physics is the foremost expert in what we call the particle and cell method, which is actually widely used in all sort of lab plasma applications. Folks doing tokamak simulations will do particle and cell, but it's actually kind of in the vein of an exact description of a plasma in the sense that you're literally solving F equals ma for every quote unquote particle in your system. And that's what I mean by this equation here. This is the electromagnetic force acting on the kth particle. The one simplification that does often get done, you're going to see my dog in the background here probably. One simplification that does get done is you do the simulation with so-called macro particles. And so every simulation particle actually represents a large number of physical particles. And that's one way of dealing with the 10 to the 12th ions per cubic meter in the ionosphere. But the idea is you do this, you can compute charge density by all of the positions of the particles that you've done. You can bin it, grid it, create a discretized version of the Poisson equation if you're doing a static simulation like Mears does. And you have effectively a self-consistent model, and that's sort of dictated here by this process. Now, there are a lot of caveats, especially in how you bin particles and weight them between different cells, so on and so forth. Please understand that I'm presenting this in a very simplified fashion. But what this allows you to do is simulate really small scale phenomena like Farley-Buneman waves, which is what Mears is doing in his 2013 paper. I have a student that's studying resonant cyclotron acceleration that produces these really flat looking ionospheric distributions. Here it's another example of a particle and cell method. These are generally very expensive to run. You only want to do this if you really need to study very detailed small scale physics that causes really sort of violent non-thermal distributions of particles. So not a lot of phenomena actually require this level of treatment. Now you can still do non-thermal simulations by actually solving this probabilistic equation that we talked about, the Boltzmann equation. And these are often referred to as phase fluid simulations in the sense that you're tracking the evolution of this distribution function F in terms of both a velocity and a configuration space. These tend to be somewhat used in ionospheric physics. I can think of one really good application, and it's shown over here. This is a classic paper on non-thermal particle behavior in the ionosphere. This is Doug Strickland's 1976 paper on energetic electron bombardment. The aurora borealis is produced by energetic electrons bombarding the atmosphere, and the energy is such that it triggers inelastic scattering, which is very energy dependent. And so even if you take this line here is basically a thermal distribution described by a drifting Maxwellian, even if you put a thermal distribution of particles in the ionosphere as it scatters down in altitude, they form these non-thermal distributions. These are not equilibrium distributions, and it's non-equilibrium by virtue of the fact of all of these inelastic scattering processes that are involved. So that's an example of where you do actually need to track a full phase space for your particles. But even so, if you look in Doug's paper, he's actually solving a steady state form of this equation here, and it's still quite expensive. The issue is that it's a 7-dimensional problem, which is not good from a numerical efficiency perspective. Yeah, so where we're going to end up, and you probably realize this from my previous discussion, is most ionospheric modeling is conducted in a fluid regime. The reasons are we're usually interested in fluid scales, and I'll say a little bit about this in a second, and also it's an efficiency issue. You can reduce your 7-dimensional equation down to 3 spatial dimensions plus time, plus a finite number of moments, basically, which describe average, macroscopic properties of the system that you're dealing with. So really the biggest decision to make when you're modeling is kind of, with regards to motions, it's kinetic versus fluid. And it's largely a decision of spatial scale. And Mark mentioned these dimensionless fluid mechanics numbers. Probably the most important one that you'll hear for discussing ionospheric physics and atmospheric physics is the Knudsen number, which is the mean free path over the scale length. As Shasha mentioned, the Knudsen number equal to 1 is what defines the exobase, where the atmosphere stops displaying sort of collective behavior and starts becoming just ballistic motion. The characteristic scaling for the atmosphere being the scale height that she had talked about before. So Knudsen number equals 1 is often just taken to be the nominal transition. That's what defines the exobase. For neutral particles, these collisions, these mean free paths, are really given by hard or soft sphere collisions. So these are really just billiard balls, banging against each other. And that's what gives the collective behavior. This happens around 450, 500 kilometers altitude. For charged particles, it's quite different. This is a very important distinction. Charged particles experience Coulomb collisions with each other. So these involve electrostatic forces. These are 1/r² forces. They're long-range forces, and the ion exobase, so to speak, is actually at around 2,000 kilometers altitude. So by and large, as long as you're dealing with systems that have relatively large scale lengths, a fluid simulation is going to be appropriate. Now, that is not the case for like the work that MERS does. And it's not going to be the case if you have a lot of sort of non-thermal inelastic processes operating in your system. So you do have to be a little bit careful. You can't just compute the Knudsen number, say that it's small, and say, therefore, I'm using fluid. That may not be the case. You have to really look at the physics that's active in your system, but it's a very good indicator. There are other length scales in a plasma. If you're below the ion inertial length, you can't use some of the drift approximations. So you got to be really careful about things like this. You can't assume quasi-neutral below the Debye length. These are all things that you learn on sort of day 1 or 2 of plasma physics. And I talked about the non-thermal processes as well. From an electromagnetic point of view, for ionospheric physics, we almost always use an electrostatic description, and that is actually somewhat difficult to defend in some cases. So I'm not going to pretend like this is always what you should be doing. What I will say is this gives sort of a 2-cell circulation pattern, sort of like you might see for southward interplanetary magnetic field. And if you map out what the current densities look like in the ionosphere due to this ohmic collisional currents that Shasha talked about, they look something like this. Whoops, wrong way. And what you'll end up with is the classic region 1, region 2 current systems. That whole process, the ionospheric closing of those currents, is really well described, particularly at larger scale, by just a simple Ohm's law, J equals sigma E. The same thing that describes motion in a normal conductor. I guess the difference is the charge carriers across the field line are positive instead of negative. So anyway, we tend to use J equals sigma E, which is pretty much a static model of momentum. Div J equals 0, which basically throws away the displacement current, infinite speed of light assumption, basically. And then we use the electrostatic assumption, E is minus grad phi. That is by far the most problematic out of all of these things. And various attempts have been made to address that, but it's actually quite a difficult modeling problem. So anyway, this is your normal E&M theory for stationary charges. This is electrostatic. For steady current, you can just solve Ampere's law. If you have rapidly varying magnetic fields, such as would be present for alphane waves impinging your system, you need an inductive model. There's a paper by Bill Lotko that explains exactly when that's necessary. And then if you have div J not equal to 0, you have to resolve the displacement current. And that's almost never done in ionospheric physics. except for radio propagation problems. Like if you're actually simulating the radio wave propagation through the ionosphere, that is a situation where obviously you can't do that without the displacement current. So by and large, we're going to use static models for this. I thought I would throw down sort of what these equations look like. This is an example of a model that describes the ionosphere, and I've got arrows going to all of the physical processes, and it's utterly overwhelming. And really, the message I want to send here is, first of all, that we are treating the ionosphere as a fluid. So you see things like, boy, this looks like a conservation of mass equation. This looks like a conservation of momentum equation. This looks like a conservation of internal energy equation. You see some familiar sort of Euler or Navier-Stokes style operations there. And those are definitely part of it. But being the ionosphere, you need separate fluids for every species. You need collisions. You need ionization by EUV and soft X-ray sources. You need gravity, pressure, electromagnetic forces, and then you have collisions between every single particle type. So ionospheric modeling is really a massive, it's computational fluid dynamics first and foremost, the way that we normally apply it. But second most, it's an accounting problem. You have all of these right-hand side interactions that describe friction between species flowing against each other, or that describe heat exchange, right? You put one thermodynamic system next to another. If they're in contact, it'll have a heat flow, a heat exchange across the boundary. You know, if you consider them to be open systems, which the different particle species are. And so really, you know, if you take two different objects and rub them together, there's an equivalent friction from that. That's this last frictional heating term here. So it's really, it's not a straightforward system by any means. And it really affects what we're able to do in terms of simulation, the fact that we have to resolve all of these types of quantities. And so I've listed some of the, you have high order transport like thermal conduction, that's important. The electrons have a high thermal speed, and so you end up, they end up transporting heat very efficiently, particularly in the direction of the magnetic field. So anyway, nothing particularly, and a lot of this is probably going to be too much detail, but I wanted to put down some quantitative stuff here. So one thing, I've got this comment here, the ionospheric equations are mixed type. If you've taken a mathematical physics course or a course in partial differential equations, you'll spend a lot of time talking about hyperbolic equations, parabolic equations, elliptic equations, and so on and so forth. Those are our major classifications for these types of equations. And actually, when we do numerical analysis, the type of equation that you're dealing with is exceedingly important. It completely dominates your decisions for what algorithms are useful for solving that particular problem. And the pathological thing about trying to model the ionosphere is that it is neither of these three things. It's neither and all. In other words, there are some terms that are hyperbolic, which are generally wave-like equations. There are terms that are parabolic, which describe you know, dissipation processes. And there are, of course, some terms that are going to be sort of steady state style problems as well. So that is a big issue. And what I'm going to do is talk a little bit about methods that are commonly used to solve these three types of problems, hyperbolic, parabolic, and elliptic terms. And then I'll discuss what is a strategy for combining those into an ionospheric simulation. You know, how do you go about breaking your problem into these constituent parts for which we have efficient algorithms to do the model's solutions? First things first, though, for doing computer simulation, you must discretize things. So I've got an example of a function that's been discretized at specific points, x0, x1, x2, x3, x4. We often use the shorthand. If it's a time index that's being discretized, it usually goes as a superscript. If it's a spatial index, it usually goes as a subscript. So these superscripts here in these equations are not powers, they're just time levels or time discretizations that have been done. And then, of course, you can have multi-dimensional data. A function of x, y, z, and t would have 3 spatial indices, I, j, k, and then a time level index, which is usually n by convention for some reason. The benefit of discretizing data is that you can turn derivatives into algebraic operations. And I've shown 2 examples of how this can be done here. For example, partial f with respect to t. You could approximate it as f of t plus delta t minus f of t minus delta t over 2 delta t. Now you can look at that formula and say, yeah, that sort of looks like the definition of derivative. I can accept that, but there's actually a certain amount of truncation error associated with it. And you should be aware of that as well when you're doing, and in this case, there's an order delta t squared term that's being truncated. So anyway, that's really the name of the game, is discretizing into what we call finite differences. You want to replace derivatives with algebraic operations over the mesh, and then solve your system of equations in very basic terms. That is what you're doing. I'm going to skip over this. This is this sort of finite difference approach is by far the most common way of discussing how we solve partial differential equations. But there's also an alternative point of view, finite volume method, which actually materially is different in certain situations because it's solving actually an integral form. I'm going to leave that by the wayside. It is useful, particularly when looking at shock solutions. I'll just say that, where you have shocks in your system, like at the Dayside magneto, or bow shock, rather. So, and I'm sorry, I know there are equations here, but you really can't discuss modeling without some idea of the mathematics that are going into this. Generally speaking, it is the case that partial differential equations are less straightforward to solve than ordinary differential equations. And it's just a matter of fact, you've got a multidimensional system. A lot of times with ordinary differential equations, you can pick a Runge-Kutta or a predictor-corrector scheme, and chances are it's going to work pretty okay for your problem. Now, that's not always the case, but that's very often the case. With partial differential equations, we need very, very specific approaches for the different equation types. So if you have an algorithm that works on a parabolic problem, for example, it probably doesn't work at all on hyperbolic. It's not even marginally stable. So you have to be extraordinarily careful with numerical stability and accuracy. And so I have the 3 canonical equations here. Hyperbolic, this is a wave equation. If you couple this with another equation, you'll get your normal wave equation. Parabolic, this is basically a heat equation. And elliptic, this is basically Laplace's or Poisson's equation. Specific forms in which these appear for the ionosphere. And if you haven't done a lot of PDEs, you may not connect from the canonical to these forms, but I'll just list them here for you. These transport terms are indeed hyperbolic terms and require hyperbolic solvers in order to resolve. So these represent mass and momentum flow in your system. The heat equation, which does appear as part of the ionospheric energy equation, is an example of a parabolic equation. And then this current continuity it looks almost like Laplace's equation. It's just different enough to cause a lot of problems. So, and I'll say, I'm going to show you some examples of basic calculations in a moment, but really this is an entire course. I can't teach you this in half an hour or whatever. You really need to take a course in it. I'm just trying to give you a taste for the kinds of things that we do and the sort of analyses that we perform. Yeah, but my caveat here, please observe. I'm going to give you some example codes. I'm going to run them, but please, these methods are the simplest possible methods that will allow you to solve these problems. They're not comprehensive and perhaps not even advisable that you use them, but I just want to give you an example and a simple code that you could work off of if you wanted to. So I'll start with elliptic problems, and I'll actually bounce out to Python here for a second and show you how this works. But if you took our canonical elliptic equation, the Laplace's equation, if you used the finite difference approximations for the derivatives, you would produce this system of equations in the center here. And what you'll realize is you have one of these equations for every single grid point, And every equation references 5 unknown quantities, these f of I plus 1j, f of ij, f of I minus 1j, and so on and so forth. So these are really adjacent cells or adjacent grid points, so to speak, in your model. And so the idea is this is really effectively a large system of equations to be solved. There's one equation for every single grid point. And you can set that up is basically a matrix problem. And I've got some notes here. If you have n grid points in the x direction and n grid points in the y direction, you have n squared unknowns. And then the matrix that actually describes a system of n squared unknowns is n squared by n squared. And so you can immediately see where this could become computationally problematic. The other issue with this is the algorithms that you use to produce direct solutions scale is number of unknowns cubed. And so you can very quickly get yourself into the 6th type of, execution times for these things. So what I did is, I actually, and I put a link to this in my slides, but I have a repository of, these are actually, I've used electromagnetic examples as ways to illustrate this, but the idea is that the solution of hyperbolic, parabolic, and elliptic equations can all be sort of demonstrated within electromagnetic theory. And like I said, I put this in the, let's see, numerical electromagnetics. So I have demonstrations of various phenomena. In fact, I included this here. So this is actually a kind of a parallel plate capacitor problem. You have 1 volt potential on the bottom row of cells, 1 volt on the top, and then you separate those plates by some amount. And this is what the electric potential looks like in this case. Now it's being solved as a finite difference system. So I'll show you that here. So I have this open in Spider. This is just a little Python code. You guys can play around with this, change the number of grid points and so on and so forth. I'll start with a 16 by 16 grid, and I'm just demonstrating some of the points that I've made down here. You don't want to write your own elliptic solver. I have done so here, and I'll execute this code and you'll see how slow it is. I've got a Jacobi iteration, a Gauss-Seidel method. These are just 2 different methods for solving the systems of equations. And then I have basically a state-of-the-art solution with this UmpPack thing, which executes in a small time compared to everything else. So you see this is a very crude discretization, but all of our methods eventually converge to the same solution. If I start increasing the number of grid points in this system, you really see the failure of these first 2 algorithms, which are legitimate solutions for this problem, but you see how long they take compared to a very specialized algorithm that's based on the UmpPack software. So that wasn't too bad. Let's see, this took 159 to do Jacobi, 113 to do Gauss-Seidel. Those are the number of iterations. But if I up this to like a 24 by 24 grid, it's going to take possibly, hopefully not too much. It's going to take quite a bit longer to do these simple algorithms like Gauss-Seidel and Jacobi. And while that's executing, I'll just make the point that there are a number of software packages that specialize specifically in elliptic steady state solutions. UmpPack and MUMPS are the ones that I've used the most, but Intel also has its own special software, Pardiso. So if you need to solve a big elliptic problem, don't use successive over-relaxation or Gauss-Seidel. It's going to be incredibly slow. There are very few problems for which I think that is a good choice. Most of the time, you're going to want to use these LU factorization schemes, unless you get over 1 million grid points, in which case you're in really bad territory, and we actually don't have good solvers for that. Yeah, so see, the Jacobi iteration has just finished. and it's cranking through Gauss-Seidel right now. So anyway, these codes are pretty simple, and the idea was to provide you all with some hands-on examples. Like if you want to see how simple solutions are done with these different codes, this shows you how to set up a sparse matrix and then pass it through these different numerical procedures. So I thought that'd be kind of an interesting and maybe slightly different thing to look at. So here's our 24 by 24 solution for that particular problem. So that's a finite difference method. That's generally the accepted way of dealing with elliptic solutions. And at the end of the day, it all boils down to solving a large matrix system of equations. So for parabolic solutions, there are several different methods that you can use that are acceptable. The simplest one is what we call a backward time centered space algorithm. So this diffusion equation, which has a first derivative in time and a second derivative in space, you can discretize it per our previous derivative approximations. The one thing to note with this, and the reason why it's a backward time algorithm, is the spatial derivative is actually evaluated at the n+1 time level. So in other words, these fn+1 terms are unknown. All of these are basically unknown at a given time level n. And so that's kind of what you're solving for. You're solving for the value of f at the n+1 time level, because it's initial value problem, for all of your grid points. But the key is you've discretized this and you've produced another system of algebraic equations that can be summarized by this guy here. And I know I'm kind of floating over this, but the point here is this is yet another system of equations, and it relies on some sort of algorithm for solving matrices. In this case, it's a tridiagonal matrix, and the known optimal way of dealing with that is called the Thomas algorithm. So anyway, I'll show you, this is actually a problem. So if I go to, whoops, this is diffusion 1D. You can download the code here. But this is a one-dimensional diffusion problem. Let me clear this out. And what it's going to show us, I may have to run this a couple of times. Yeah, it's completely obfuscated by Zoom. Okay, so it's going to show us initial condition where you have you can think of this as a region where there's basically a lot of heat and there's a conducting object. In this case, this is actually magnetic diffusion. And if you let the system go, the heat or the magnetic field, as the case may be, actually tends to spread out in time. So this is a numerical solution to the magnetic diffusion equation, and it's actually based on this problem from an EM textbook that takes like 2 days to solve by hand. But if you're good coding, you can write a code in 20 minutes to solve it. This is how, yeah, right tool for the right job. So anyway, this is characteristic of any type of diffusion problem, is things spread out with time. And that's kind of the key behavior with the electron energy in the ionosphere. Shasha talked about sources and sinks for electron energy, but there's also a really high thermal conductivity, so it does tend to spread out with time. So again, we're just sort of collecting elemental solutions that can be built into something more complicated later on, which I'm not really going to show you the full process, but I want to give you some stuff to play with. There's a two-dimensional diffusion problem. I'll just run this. This is actually another problem that I give on homework, but there's basically a uniformly magnetized sphere embedded in a region of conductivity. And so you'll see initial magnetic field here. And then when the simulation starts, you'll see it evolve with time. I suppose I could make this bigger. Sorry about that. So anyway, as you watch this, you'll see it's, oh my goodness. I actually think I crashed it. Let me restart this one. I think I caused my it wasn't updating in time for whatever reason. There we go. So this is 0.02 seconds. Let's see, it should pause for a few seconds and then start running. Yeah, I know coding with the audience is always dangerous. I teach a numerical methods class, and I do a lot of this kind of stuff, and I actually kind of enjoy it as a type of instruction. Why won't this run? Oh well, let me take out this pause command that's causing it to freak out. So at least you can see it update in time. Okay, here we go. It's just slow as molasses. Okay, it dies when I resize the figure. So I won't do that. All right, so we'll just watch it sort of small. You can see the magnetic field sort of spreading out in time. And because it's a 2D problem, it actually takes a bit of a while to update, but the diffusion of magnetic field through a conductor, it's just going to spread out with time and tend to become more uniform. So it's just a little demo of, and you can see this isn't a huge code here, how you would solve a two-dimensional problem. All right, so hyperbolic. And I know I'm stepping through this quickly, but I want to get to the end where I explain how to combine all of these ideas together. So wave equations, hyperbolic equations, electromagnetic wave is the sort of canonical form. These also describe sound waves, surface waves, any type of wave you can imagine is more or less described by a hyperbolic equation of this form. Hyperbolic equations are particularly problematic. The most obvious approaches that you could take don't work at all. They're numerically unstable. So anything along the lines of the diffusion solution that we did before with just a simple finite difference method is going to be either numerically unstable, or the solutions are going to have such a large amount of error that they're going to be totally unusable. So hyperbolic problems require particularly close attention. The first algorithm to stably solve this without artifacts was developed by Godunov in 1959. And I mean, it's no stretch to say this actually revolutionized the field of computational fluid dynamics. And even today, the best methods for capturing shocks are based on this idea of upwinding, where you take the spatial derivative in the upwind direction. If you include downwind information, it destabilizes the algorithm. So these upwinded methods are the best choice for capturing shock-like solutions, but this is only first order in space and time. So this Godunov method is actually totally unacceptable. It's very diffusive, and it doesn't, your wave will actually just spread out with time because of numerical diffusion. So really you have to pick a high resolution, higher order methods, and there are many of these. Or if you don't have shocks, you can do something like Lax-Windroff or finite difference time domain. And I just mention these names because these are methods that you can look up if you have a solution that isn't a shock that you're trying to model. FDTD, finite difference time domain, is really heavily used in electromagnetic simulation. It does have the disadvantage of being a staggered mesh, so you have to keep two sets of data that are offset on your mesh. That's kind of the basis of that algorithm. But it's basically sort of a leapfrog in time type method. So anyway, I can show you some, I put some numerical codes for waves in one dimension. I guess I don't dare try to resize the window because for whatever reason, it doesn't start. All right, so this is just a wave packet propagated. So this is electromagnetic field, electric field on top, magnetic field on bottom. They're perfectly in phase. It's a non-dispersive media, non-conductive medium. And as typical with waves, it's going to propagate with a set shape without losing its shape. So it's conveying energy and momentum and information in a particular direction. I used a periodic boundary here, so it just goes out the right end and back in the left end as well. Doesn't change shape, doesn't lose its form. Now, you can do a poor job of resolving waves. For example, if your resolution is bad, let me reset. So I did 96 grid points. If I make that like 48, if I half the number of grid points here, what you're going to see, I'll try to run it. This is an example of a poorly resolved simulation. So you can see my wave packet looks pretty choppy, but what it's going to do is something totally unphysical. You see how the amplitude is decreasing with time? That is not physical for an electromagnetic wave in a vacuum, which is what is happening here. It does not, a perfect plane wave does not decrease with time. This is an artifact of the resolution. And this shows if you don't properly have enough grid points, you know, within your wave packet to fully resolve things, you end up with these totally unphysical types of behavior. And this is what we call numerical diffusion. It's a spreading of the wave packet that's due to basically the implementation of the algorithm and the fact that you haven't resolved the wave well. This is a very common feature in models. You will see this all the time. It's completely unphysical. It means you don't have enough resolution in your system is what it means. You're basically damping out wave modes of interest. So you do need to be very careful and very aware of that. So 48 grid points is not enough. 96 didn't look great either, but at least we didn't have that kind of problem with it. All right, I'm almost done here. I had one more demo that's a two-dimensional electromagnetic wave produced from some sort of source of radiation in the center, but this is also solved using a Lax-Wendroff type of method. This one is really slow. I may not even let this run for very long, but what you can see is the part of this that corresponds to a radiation field is emitted from the center and expanding in a ring from the very center of the domain. So, you know, if you did want to, someone asked the question of how you get started with doing numerical stuff, you could play around with codes like this. You could read about the methods that I'm using. You could sort of practice and get a feel for how they let you solve, in this case, electromagnetic problems, but also plasma physics and ionospheric physics types of problems as well. So that's why I wanted to give those to you. And again, I know this is like massive amounts of information, but so this is, I presume you'll be given the slides and you can just follow this repository. I use this in some of my courses. I also give this to my students who are going to do modeling stuff, who are trying to get started. And I've been told that it's somewhat useful for that. The last thing that I have to discuss here is really kind of wrapping up. You know, I showed you a bunch of electromagnetic solutions that are elemental problems like wave propagation, magnetic diffusion, or an electrostatic problem that we looked at. But the ionospheric equations are none of those, or all of those type of equations. So there's this exceedingly important result from numerical analysis. I would argue it's probably the single most important thing to know about numerical implementations of PDEs. It's called operator splitting, and I don't have time to discuss why this works. And it's actually one of those things, the first time I saw this, I didn't believe that this worked, but it does. And almost all codes are based on this idea of operator splitting. And the idea is you can take a mixed type of equation. So here's an energy equation that's actually pretty similar to what we solve in the ionosphere. There's a transport hyperbolic term here that describes the flow of internal energy. There's a source term here that's basically adiabatic expansion. And there's a term here, which I may have the wrong sign for. No, it's the right sign, which describes the heat conduction, basically. So it's the worst possible thing. It's hyperbolic with source terms with parabolic term, effectively. It's sort of all of the above. So the way that operator splitting works is you can solve pieces of this problem one at a time, and then take what we call a partially updated solution and pass it into the next algorithm. And here's how this works. So suppose I take the hyperbolic part of this equation and just represent it by itself. So here's d by dt of internal energy is minus basically the flow of internal energy. If I solve this equation, this is a pure hyperbolic equation. If I solve this using, say, Lax-Windroff, like the previous example, I'll produce what I call a partial update for the internal energy density. So this is rho E star. This partial update can be put into the next operator in the sequence. So the next operator in the sequence, you always carry the time derivative and you pull this adiabatic compression expansion term. I use as input to this adiabatic solution the partially updated solution from the transport step, and then I update it again and I get a second partially updated solution. That second partially updated solution is used finally in this heat conduction solution, and I get a full update to the n+1 time level. So I'm actually picking off the operators and solving them one at a time. And again, the first time I saw this, I couldn't believe this works, but this is used in almost every single CFD code you'll ever look at. It's called operator splitting, and particularly for linear problems, it basically works perfectly. For nonlinear problems, you have to be careful with time scales associated with each of these operations. Like some of these may be stiffer terms than others, they may have shorter time scales. Generally speaking, you want to resolve those last. But anyway, I don't have a example per se of this, but I will say that the 2D problems, I actually used a directional split for transport on the X and Y. So it is, in a way, in some of those examples, I am using the split operator approach. I'm out of time, right? Yeah. Okay.
Yeah, we're pretty. I was just about to interrupt and find out where you were. Christina had to step away, so.
Oh, that's okay. I have some future slides here, but I'll let everyone look at these. These are just sort of what I think we kind of need to do for future modeling projects. And I was thinking, for those of you who are students, these are things that, maybe you all will solve these problems that I think that we have, as part of your research in your future. So I'll let you guys, you all flip through those on the slides. Sorry, go ahead.
Pick one.
Pick one. All right.
Talk about it.
We talked about mesh refinement a little bit, so I'm going to leave that alone. I think we all know we need more resolution, and I showed some examples of why. I'll focus on this one. I think we have a problem with data constraints. And what I mean by that is something that actually Nick asked me about earlier. What do you do on the sides of your simulation box? And the answer is frantically wave my hands around and hope that I can put the boundary far away enough so that it doesn't completely butcher the solution in the region of interest that I'm interested in. And so I think there are several ways of dealing with this. Having mesh refinement schemes is one of them, where you have sort of smaller models with maybe even different physics embedded inside other models. Another way of doing it is to say, forget it, there's no way I can actually solve this, or it's too technically painful to have the computing resources to actually do the mesh refinement that I need to do, or the nested modeling that I need to do. You could think about having data constraints, based on like in this case, this is a constellation of satellites that we were going to use to define boundary conditions for a simulation of ionospheric currents. And so if you have distributed measurements, you could come up with a data product that would be appropriate for sort of constructing inputs for models. And that's something that we sort of have tried to do. This is something that we're interested in doing with GDC. If you have a distributed measurement, you could think about creating a map of inputs for your models. This is something we've tried to do with detecting like earthquake sources and TEC data. But I think it's a really useful way of using the models, because after all, for example, GDC is not going to measure inside the ionosphere. It's actually going to measure more or less at the top of the ionosphere. We need models to sort of fill in the gaps below that to understand what the full response is. And so that's kind of what I perceive is one of the future needs. The modeling needs to come closer to the data and become sort of a really quantitative tool, not just something that you fiddle with the knobs, but something that you actually put the data in a sense. So that's it. Magic.
Oh, that was with the parameter.
Oh yeah, moving the knobs around. I just
right,
change it until it agrees. That's not. I mean, we do that. Everyone knows that modelers do that, right? Like, oh, it doesn't agree with the data. We have 18,000 parameters we can change. That's really not science. But I'm not going to say it's not a useful thing to do, because sometimes it gives you an understanding of, wow, the plasma turbulence is really sensitive to electric field. Like you learn stuff like that, but it's not really science. It's more like, I don't know. I shouldn't say it's not science. It's playing around.
You learn things from it in a structured way, and so it is a structured exploration that gives you insight. So
that is true, but the conclusions are very difficult to draw from that type of activity. Like you get a basic feel for system responses, but you can't twiddle 1,800 knobs on the inputs and then say you've explained why this happens. That's sort of like when if you want to get at causality, it's a dangerous way to try that, is what I would say.
Okay, great.
So I'm happy to answer questions, and
yep.
Like I can forward my email, and I'm happy for that to be distributed. I forgot to put that in the slides, but these codes that I showed you are available. You can play around with them, ask me questions about them. I created them as demos for some of my students, and I think they're sort of useful demonstrations of how you would construct a model, but without all of the complexity that's actually in an ionospheric model. Like if you look at my source code for Gemini, it's very complicated, but I can write a 100-line Python script that illustrates some of the basic ideas. Data assimilation is a huge deal. And did I even mention that here? I should have, actually. This slide.
Before you get into that, let me give a little bit of instruction. So yes, please put questions into the chat. You have, so for tomorrow, we have a lab, Matt, on using the CTIPI model, or we're going to use results of the CTIPI model to explore variations in the ionosphere, the structure of the ionosphere, and variations in the ionosphere. So there is a time zone group assignment for that you should look at over the participants should look at over the next 20 hours or so at some point in time as preparation for then going further. It's just part one of the manual that I put together. Part two we'll do tomorrow as a group. And be prepared to interact tomorrow. We'll also have a brainstorming session on around the decadal survey and what the decadal survey is and what you might like to see in the decadal survey as people who are coming of age in this scientific community in the next decade. But questions for Matt. So Matt's going to take a question. We've got a question already from Miguel on data assimilation. Actually, I need to read some papers. So yeah, so I was going to say the other thing, you rattled off a whole bunch of references, I think, in part one that might be useful to pass along in maybe the Slack channel.
Oh, I didn't realize we had one. Yeah, I can.
I will make sure you're invited to the Slack channel again.
Oh, great. Yeah, and I had a really chaotic week last week, and so I apologize again for not being as as much of a participant up to this point. But yeah, so data assimilation is so what data assimilation is you have a notional simulation, so to speak, for how you believe that a system works. And then you run this for a while, you have some data that describes that is effectively the same as some parameter that you're simulating, and you use that data to make a correction onto the actual physical simulation that's running. And the process of making the correction is actually fairly complicated. Sometimes it's done with a Kalman filter. Sometimes there's some other type of methodology that's used to do it. But it's a statistical framework, basically, for including data within models. And I think it's very potentially useful for the types of simulations that we do. The big problem is really data coverage. And I think GDC is going to go a long way towards kind of addressing this in a global context, you know, having measurements from orbital planes that are well separated in different places around the Earth. But assimilation also requires that you be able to run a model efficiently over and over again. And for some models that's possible, for others it's not. But this is a technique that's widely used in like numerical weather prediction, for example. They use assimilative models in addition to predictive models. And this is, you know, something that our community should be doing more of, especially in the ionospheric side of things. There are assimilative ionospheric models like GAME, for example. There's a GAME that's developed by Utah State University that's used by the Air Force. That's an assimilation model, for example. So yeah, that's a really good question. And yeah, I need to read some more papers. I apologize if that was, I was trying to sum up a bunch of stuff that you could sort of sink your teeth into later, but it may have just ended up being kind of overwhelming at the end of the day. Parameterizations of gravity waves. So the question is, how good are parameterizations of gravity waves from the lower atmosphere in ionospheric models? The answer is absolutely terrible. There are parameterizations over some parts of the spectrum of gravity waves. Erdal-Yeat has done some work in probably the last 10, 15 years on parameterizing gravity waves for general circulation models. And there's been some success in doing that, but the parameterizations are very challenging to come up with, right? You need some data to base that on. And sometimes you can put in a parameterization and make your agreement with data even worse than it was without the parameterization. So this is an ongoing field of study. You know, how do we get energy and momentum carried by subgrid waves into the bottom of our ionospheric and atmospheric models? So not particularly good. I think, let's see, Eric Becker, I believe, has tried to do this as well, where there's some parameterization of small scale waves in his, what is it, MIAMCM model or something like that. So that is, I would say, check out Eric Becker's papers and check out Erdal-Yeat's papers. Those are what I know of recent work that's been done on that topic. And my understanding is it's a very hard to do this. And yeah, Haya MCM, thank you. Appreciate it. Yeah, that's Eric Becker's model. So he has some parameterization of waves as well. But I would recommend you check out those papers, and that will sort of fill you in on what the state of the art is. But my impression is that it's very hard to do correctly. There need to be more data sources in order to specify what those wave fields should look like. Incidentally, there's a NASA mission that will be flying on the International Space Station, atmospheric wave experiment, that's going to do imaging of a lot of those waves. And I think my impression is that's going to actually help improve some of those parameterizations a lot. But that's a good area to get into. I think there's a lot of momentum and energy that's coming up in the form of small scale waves that's basically unaccounted for in the models. And it's probably causing a lot of the day-to-day variability that we can't reconstruct or simulate properly, but that we see in the data. That's my speculation. Mission, yep. I forget when it launches. It's actually, what, 2025 maybe? 2026? it's coming soon. So that, if you were to do research in that area, it's extremely timely. You'll have a beautiful data source available in the next couple of years. Knock on wood. Every launch goes perfectly. I think, does WHAM have a gravity wave parameterization? I don't know if it does or not. Anyway, sorry.
I don't. Yeah, I don't know. So I know that that was I saw a talk from Two-Way Fang at NOAA
Yeah.
on the Starlink issue,
Yeah.
which actually we spent a little bit of time looking at that event earlier in the summer school, and so it was not a very exciting event. It was
It was relatively pedestrian, but at the same time, if you're doing very LEO stuff, man, you got to be really aware of these things.
Mhm.
Like those types of storms are not uncommon. And if you're going to launch into very low Earth orbit, you need to be really careful.
and so the state of the art at least the state of the operations, I should say, which is, as we were discussing, different from the state of the art, right? It
Yep.
was WHAM is a version of WHAM that they're running at SWPC, and apparently the SpaceX people were using an older MSIS model.
Oh, MSIS. So MSIS will give you storm responses, but they're gonna miss the highs and lows, and I think that's the problem.
Uh-huh.
Like if you look at a WHAM simulation during a strong storm, it's going to show more of a peak in the increase in thermospheric density in LEO than MSIS would, I would assume. The other thing is there are known issues with MSIS, and I haven't used 2.0 a lot, but I know a lot of work was done comparing data to MSIS 2000, and it has some serious shortcomings in certain types of situations. And so, I mean, it was the best thing we had until MSIS 2.0, but it was known to not be super great in some situations.
And
I'm trying to think of sorry, go ahead.
Well, so I'm just thinking about the lab that we're running tomorrow. One of the things that's important for the various inputs for MSIS and NCTIPI, they take these global inputs or they take indices as inputs.
Yep.
Of F10.7 and
KP
and AP,
right? Probably.
Yeah, and so I'm both curious about what is your opinion on that? What's your opinion on F10.7 versus actual EUV flux as
Yeah,
as
these are good questions. I think that I haven't played around with the EUV and X-ray fluxes, but I presume during these flare events that if you're not using an actual measurement, you're really getting it wrong, because you're going to have order of magnitude increase in X-ray fluxes and stuff like that, and so that's going to really beat up the lower thermosphere and middle atmosphere. Global indices, I mean, the thing is, what else are you going to use, I guess, for a global model? It's like, I mean, of course, a single number, the DST index or the AP index or the KP index is not going to describe the complexity of, how the magnetosphere is twisting itself up or whatever the case may be. So it's never going to be awesome, but at the same time, like, I'm not sure what kind of convection model CTIP-E uses, but they may have parameterized it fairly well as a function of AP index or something, or IMF orientation or whatever, and it may be pretty good. I don't actually know. I think that metrics for deciding when models have done a good job and when they haven't is kind of an emerging field. Like the numerical weather prediction folks have done this for a long time. They know when they're wrong and when they're right. But in our field, I mean, a lot of times we'll get within a factor of 2 and man, that's good. I'm happy with that. Yeah, of course, that's from an operational perspective, that's totally unacceptable. Like you can't make any decisions based off of that. Well, I mean, it depends on what it is, but yeah, so that's a rambling response. I mean, my impression is that a global index is not going to do as good a job as like having a physics-based magnetosphere model tacked onto it, actually producing, you know, the geomagnetic currents and you know, so on and so forth. Yeah, one of the questions actually, so what are the relevant magnetospheric parameters that generate changes in the ionosphere? The open-close field line boundary is kind of a good thing to keep an eye on because that sort of determines the size of the polar cap. A lot of times it will dictate the cross-polar cap potential, which in some sense tells you how much energy is available to sort of flow into the ionosphere. So that's a good one. You could look at the departure of, this is good when you're looking at like GOES data. If you look at the stretching of the tail of the magnetosphere, that's a good indication that energy is being stored in sort of the plasma sheet cross-tail current. And oftentimes you'll see that energy storage sort of ramp up, and a lot of times it'll be coincident with like the growth phase of a substorm or something like that. So looking at tail configuration is really important. You know, you store inductive energy in the tail and then it gets released as a substorm sometimes. The status of the ring current has an enormous effect on the Earth's magnetic field. In fact, I think the DST index is almost completely dependent on what the ring current is doing. So, you know, that gives you an idea of the state of the energetic radiation, energetic particles in the inner magnetosphere. Magnetopause distance is a good one. You know, when the magnetosphere gets really compressed, you can almost always see some change in global geomagnetic activity associated with that. So that's going to depend on IMF orientation and ram pressure of the solar wind. So that's, you know, something that can be, you can use like discover data to get an idea of when a high pressure pulse is coming or something like that. Particle environments are somewhat difficult to deal with. You know, what is the precipitation that's coming into the auroral zone? That's pretty hard to predict. Our best models are empirical. Probably Ovation Prime is one of the better ones. And it's very crude in terms of resolution. So the particle environments, I would say, are not super well described. And of course, everything matters, right? If you want to model the ionosphere, you have to know all of that stuff in principle, right?
I think that's one of the both interesting but challenging things about it. I always refer to ionosphere physics as spear and magic helmet physics, because, you know, just when I think I've got the an eye on things, you know, the ionosphere physicist as the dungeon master comes in and says, but you've forgotten about the special, you know, anomalous, you know, blah 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 reconnection, or not recombination thing over here with this like one like minor species that then somehow has this cascading
yeah,
event.
I feel like that with the middle atmospheric folks. It's like like the amount of chemistry required to understand like what radiation belt particles do to the middle atmosphere is like it gives me anxiety when I start
What,
seeing the reactions, and I'm not a chemistry
what
person.
radiation belt particles do the middle
Well,
out?
so what is it? Medium range energetic particle precipitation
Oh.
has all of these effects on odd nitrogen and hydrogen in the middle atmosphere. And it's like, I forget exactly what the particular importance is, but anyway, it's just this absolute zoo of chemistry. And it like,
And these are these are high energy, KeV and MeV particles coming in from the radiation belts.
yeah, I think they're MEV range particles. And yeah, the
Oh
radiation
wow!
belts are going to be one of the sources. So this is, it's Cora Randall has done a ton of work on this. Let's see. Let me see if I can get a good like review paper I can drop in the.
And of course, there are any other questions that we have from Matt while we're in office hours is great. And for those who are dropping off, I'll see you tomorrow.
Yeah, I'm trying to find a good. Let's see, a new parameterization. Oh, let's see. Go into Google Scholar and type Cora Randall energetic precipitation, and you'll see about 10 papers ish that talk about various aspects of this problem. And I don't actually understand it enough to describe it beyond what I've told you.
Okay.
But it's actually another aspect of space weather where you have these like stratospheric and mesospheric effects from the particles. Yeah. I think, her work over the past decade, 15 years is like sort of given us an understanding that this process was a lot more important than people, understood before. So yeah, thanks everyone for listening. And like I said, I'm happy to take more questions. And I apologize if that was too much crammed into too little time, but
there's always for anything like this, there's always too much to cover, and there's always more, right? And so
yeah, I'm happy if folks, if anyone has a question, like, someone asked earlier about, how do you get started with particular modeling projects? And I'm happy to expand. If you want to drop me an email, I can tell you more details of how I got started. And, I can tell you if you have a particular problem in mind, references. And I think the hard part with modeling is we don't have the Mike Kelly Ionosphere book of modeling, right? The one reference you can go and get like 80% of what you need. That doesn't exist. It's all spread about in applied math textbooks and, mathematics for engineering and computer programming and blah, blah, blah. It's really, I think getting started with modeling is actually much harder than just getting rooted in the basic physics because of this issue.
sounds like you need to write a book.
Someone should do it. Yeah, I haven't even been able to write a paper on my model. I mean, I have papers using results from my models, but I don't have a paper that describes exactly what I do in the model in full detail. And that's actually a bit of a problem. Once I get that done, then maybe I'll think about it. I have documentation on our GitHub site that's this like 50-page document that tries to explain how all of these equations are solved, but it's not good enough. Like if you read it, you would have to already know very well what you're looking at to understand it.
All right. Well, I don't see any other questions. And
I'll drop my email in the chat, and
yep.
Nick, you can distribute it.
And I just sent you another invite to the Slack channel.
Yeah, let me see if I can find that this time. Sometimes that stuff